Look around you. The chair you're sitting in, the walls around you, the air you're breathing, the ground beneath your feet. Now, in your mind, zoom out. Picture your city from above. Keep going. See your country, then the curve of the earth, that blue marble hanging in the darkness. Keep zooming. Watch the earth shrink to a dot as the sun comes into view. Keep going further. The sun becomes just another star among billions in the spiral arms of the Milky Way galaxy. Don't stop. Watch our galaxy become a smudge of light among 2 trillion other galaxies scattered across the observable universe. Everything you have ever known, every person who has ever lived, every star that has ever burned, every atom that has ever existed. What if all of it, every last bit of it, is trapped inside the universe's most terrifying object? What if we are all living inside a black hole? Now, before you click away thinking this is science fiction, stay with me. Because what I'm about to tell you is not a wild theory from the edges of the internet. This idea has been seriously studied by physicists at major universities for over 50 years. It has been published in some of the most respected scientific journals in the world. And in 2025, new evidence from the James Webb Space Telescope may have given this strange idea its strongest support yet. This is the story of how our entire universe might be the inside of a cosmic prison, and why that possibility is actually good news. Let's start with a question that has haunted scientists since Albert Einstein published his theory of general relativity in 1915. How did our universe begin? The standard answer goes something like this. About 13.8 billion years ago, everything that exists was compressed into an unimaginably tiny point. This point was infinitely dense and infinitely hot. Then, for reasons we do not fully understand, it exploded. Space itself began to expand. Matter cooled and clumped together. Stars ignited, galaxies formed, planets coalesced, and eventually, on one small rocky world orbiting an ordinary yellow star, life emerged and began asking questions about where it came from. We call this the Big Bang. It's a beautiful story. It explains so much about what we observe: the expansion of space, the cosmic microwave background radiation left over from the early universe, the abundance of light elements like hydrogen and helium. The Big Bang is one of the most successful theories in all of science. But there's a problem, a big one. At the very beginning of the Big Bang story, there's a moment where everything breaks down. When we trace the expansion backward and backward, we eventually reach a point where all the matter and energy in the universe is crushed into a space smaller than an atom. At this point, the equations of physics simply stop working. The temperature becomes infinite. The density becomes infinite. Time itself loses meaning. Physicists call this a singularity, and they hate singularities. In science, infinity is usually a warning sign that something has gone wrong with your theory. Here's the thing. There's another place in the universe where we find singularities. At the heart of every black hole. Black holes and the Big Bang share this uncomfortable mathematical feature. Both involve points of infinite density where our understanding of physics collapses. This similarity has nagged at scientists for decades. It feels like too much of a coincidence. What if it's not a coincidence at all? What if the Big Bang and black holes are actually the same kind of thing, seen from different angles? To understand this idea, we need to talk about what black holes actually are. When a massive star, one at least 20 times heavier than our sun, runs out of fuel, something catastrophic happens. The nuclear reactions in its core that have been pushing outward against gravity suddenly stop. With nothing to hold it up, the star's core collapses in on itself. The outer layers come crashing down and then rebound outward in a spectacular explosion called a supernova. But the core keeps falling inward. If there's enough mass, nothing can stop the collapse. Not the pressure of atoms being squeezed together. Not even the weird quantum mechanical rules that normally prevent matter from being compressed beyond a certain point. The matter just keeps falling and falling, crushed into a smaller and smaller space. Eventually, the gravity becomes so intense that even light cannot escape. Picture throwing a ball into the air. On Earth, it comes back down. On the Moon, with weaker gravity, you could throw it higher. On a small asteroid, you might throw it fast enough that it escapes into space forever. Now, imagine a place where gravity is so strong that you would need to throw something faster than the speed of light for it to escape. Since nothing can travel faster than light, nothing gets out. Ever. The boundary around this region is called the event horizon. It's not a physical surface you could touch. It's a point of no return. Cross it, and you are forever cut off from the rest of the universe. No signal you send could ever reach the outside world. To anyone watching from a safe distance, you simply disappear. This is a black hole, a region of space where gravity has won completely. Now here's where things get strange. In 1916, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I. Despite the chaos of war, he found time to solve Einstein's complex equations of general relativity for the simplest possible case, the gravitational field around a perfectly spherical, non-rotating mass. His solution described what we now call a black hole, though Schwarzschild himself died before anyone realized the full implications of his mathematics. One of the key features of his solution is a quantity called the Schwarzschild radius. This is the size an object would need to be compressed to in order to become a black hole. For the Earth, this would be about 9 millimeters, smaller than a marble. For the Sun, it would be about 3 kilometers. The more mass you have, the larger the Schwarzschild radius. Here's the formula. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. It's simple enough to calculate on the back of an envelope. And when scientists plugged in the estimated mass of the entire observable universe, about 10 to the power of 53 kilograms, or a 1 followed by 53 zeros, they got a very surprising answer. The Schwarzschild radius of all the matter in the observable universe works out to roughly 13.8 billion light-years. That number should sound familiar. It's almost exactly the same as the radius of the observable universe itself. In other words, if you took all the matter we can see and calculated how large a black hole it would make, you would get a black hole the size of the universe we actually live in. The mass of our cosmos and the size of our cosmos match up in exactly the way you would expect if we were living inside a black hole. The famous physicist Michio Kaku has joked about this. If you want to know what it looks like inside a black hole, look around your room. Now, scientists have debated whether this is truly a meaningful coincidence or just a quirk of mathematics. The physicist Sean Carroll has argued that this relationship is a direct consequence of having a spatially flat universe. It follows automatically from the equations of cosmology. But even Carroll admits that this just pushes the question back a step. Why is the universe flat in the first place? Something strange is going on here. And some physicists think the explanation might be exactly what it looks like. We really are inside a black hole. This idea has a long history, and it's more respectable than you might think. In 1972, a physicist named Raj Pathria published a paper in the prestigious journal Nature with a provocative title, "The Universe as a Black Hole." Pathria compared the mathematics of a closed universe, one that curves back on itself like the surface of a sphere, with the mathematics of the region inside a black hole. He found that the two descriptions could be made to match up perfectly. Our universe, he suggested, might not only be finite and closed, but might actually be confined inside a black hole located in some larger external space. The idea was intriguing, but Pathria couldn't explain how such a universe would form or why it would be expanding instead of collapsing. The theory sat in the margins of cosmology for 2 decades. Then, in 1992, a theoretical physicist named Lee Smolin at the Perimeter Institute in Canada took the idea in a radical new direction. Smolin proposed something he called cosmological natural selection. In his model, every black hole that forms in our universe creates a new baby universe on the other side of its event horizon. These baby universes would have their own stars, their own galaxies, and their own black holes, which would in turn create more baby universes. It was cosmic reproduction on a scale that boggles the mind. Smolin's theory was speculative, but it had a remarkable feature. It made testable predictions, and some of those predictions have since been confirmed by observation. The idea gained more traction in 2010 when Nikodem Popławski, a Polish theoretical physicist at the University of New Haven, published a series of papers showing how universes could actually form inside black holes. Popławski used a version of Einstein's theory that includes a property of space-time called torsion. At extremely high densities, this torsion creates a repulsive force that prevents matter from collapsing all the way to a singularity. Instead of crushing to a point of infinite density, the matter bounces. This bounce could be the Big Bang. National Geographic and Science magazine both named Popławski's work one of the top 10 scientific discoveries of 2010. Most recently, in June 2025, a team led by Professor Enrique Gastiñaga at the University of Portsmouth published a new black hole universe model in the journal Physical Review D. This model proposes that our cosmos formed inside a massive black hole in a larger parent universe. The research team ran simulations showing how a collapsing cloud of matter could avoid forming a singularity, bounce at extremely high density, and begin expanding, creating exactly the kind of universe we observe around us. The Big Bang model begins with a point of infinite density where the laws of physics break down, Gastiñaga explained. This is a deep theoretical problem that suggests the beginning of the universe is not fully understood. We've questioned that model and tackled questions from a different angle by looking inward instead of outward. So, let's be clear about what we're discussing here. This is not fringe science. This is not speculation from anonymous blogs or YouTube channels. Black hole cosmology has been published in Nature, Physical Review D, the Astrophysical Journal, and other top-tier scientific publications. It has been developed by physicists at major research institutions around the world. It makes specific, testable predictions that can be checked against observations. Is it proven? No. The standard Big Bang model remains the consensus view among cosmologists. But the black hole universe hypothesis is a legitimate scientific alternative that addresses some deep problems with our current understanding. The Big Bang theory, for all its success, has always had a gaping hole at its center: the singularity. The moment of creation is hidden behind a curtain of infinities where our physics cannot reach. Black hole cosmology offers a way to peek behind that curtain. Instead of a beginning from nothing, it offers a beginning from something, a transformation rather than a creation. If this theory is correct, then the Big Bang was not the birth of existence. It was a birth within existence. Our universe came from somewhere. It has a parent. and every black hole in our night sky might be the nursery of another cosmos. In the sections ahead, we're going to explore this idea in depth. We'll examine the evidence for and against it. We'll meet the scientists who have dedicated their careers to this strange possibility. We'll discover what this theory says about the nature of reality, the fate of information, and the ultimate structure of existence. And we'll confront the dizzying implication that there might be universes inside us, in the hearts of black holes scattered throughout our own cosmos, that we will never, ever be able to see. Welcome to the universe, or should I say, welcome to the black hole. Let's begin. Before we can understand how our entire universe might exist inside a black hole, we need to understand what a black hole actually is, and not the science fiction version, the real thing as described by the mathematics of Einstein's general relativity. The story begins in 1915, when Albert Einstein published his general theory of relativity. This theory revolutionized our understanding of gravity. Newton had described gravity as a force pulling objects toward each other across empty space. Einstein showed that gravity was something far stranger. It was the bending of space-time itself. Massive objects like stars and planets curve the fabric of the universe, and other objects simply follow these curves. Einstein's equations were beautiful, but fiendishly difficult to solve. So when a German physicist named Karl Schwarzschild managed to find an exact solution just a few months later, in early 1916, it was a remarkable achievement. Even more remarkable was that Schwarzschild accomplished this while serving as an artillery officer on the Russian front during World War I. He would die of a rare skin disease just months after sending his calculations to Einstein. Schwarzschild's solution described something that seemed impossible, a region of space where gravity became so strong that nothing, not even light, could escape. At the time, most physicists, including Einstein himself, thought this was merely a mathematical curiosity with no physical reality. They were wrong. What Schwarzschild had discovered was the black hole. Let's build one in our minds, layer by layer. At the very center lies the singularity. This is a point where all the mass of the black hole is compressed to infinite density and zero volume. Here, the curvature of space-time becomes infinite. The laws of physics as we understand them simply stop working. Temperature, pressure, density, all the familiar quantities that describe matter become meaningless. The singularity is a place where our equations produce nothing but infinities, which is mathematics' way of telling us something has gone terribly wrong with our theory. For a non-rotating black hole, this singularity is a point. For a rotating black hole, which, as it turns out, describes every black hole we have ever observed, the singularity stretches into a ring. But in both cases, the singularity represents the ultimate unknowable, a curtain beyond which our physics cannot see. Surrounding the singularity is the event horizon. This is not a physical surface you could touch. It's a boundary defined by gravity. At the event horizon, the escape velocity, the speed you would need to travel to break free of the gravitational pull, equals the speed of light. Since nothing can travel faster than light, anything that crosses the event horizon is trapped forever. Think of it this way. Imagine you're standing on the shore of a river, and the current gets stronger the closer you get to a waterfall. At some point, the current becomes so powerful that even the fastest swimmer cannot escape being pulled over the edge. The event horizon is like that point of no return, except instead of water current, it's space-time itself flowing toward the singularity. The radius of the event horizon is called the Schwarzschild radius. For our Sun, if you could somehow compress all its mass into a black hole, the Schwarzschild radius would be about 3 kilometers. For the Earth, it would be about 9 millimeters, smaller than a marble. The more mass, the larger the Schwarzschild radius. Moving outward, we encounter the photon sphere. This is a shell located at exactly 1.5 times the Schwarzschild radius. At this distance, gravity is so strong that light itself can orbit the black hole. Photons here travel in circles, trapped in an unstable equilibrium. A slight push inward, and they spiral into the event horizon. A slight push outward, and they escape into space. When you look at the famous images of black holes captured by the Event Horizon Telescope, that glowing ring of fire around a dark center, you're seeing light from the photon sphere. The light from the accretion disk, that swirling ring of superheated gas falling into the black hole, gets bent and twisted by gravity. Some of it orbits the black hole multiple times before escaping toward us, creating thin, bright rings around the central shadow. If you were an astronaut hovering just outside the photon sphere and you looked straight ahead, you would see the back of your own head, because light from behind you would curve all the way around the black hole and return to your eyes. For spinning black holes, what physicists call Kerr black holes, named after the New Zealand mathematician Roy Kerr, who solved the equations in 1963. There is an additional region called the ergosphere. This is a zone outside the event horizon where space-time itself is being dragged around by the rotating black hole. It's shaped like a flattened sphere, wider at the equator than at the poles. Inside the ergosphere, nothing can remain stationary relative to the distant stars. Space is flowing around the black hole like water going down a drain, and everything gets swept along. But here's the remarkable thing. You can still escape from the ergosphere. The event horizon is still further in, and if you enter the ergosphere with just the right trajectory, you can steal energy from the black hole's rotation and escape with more energy than you came in with. This process, proposed by Roger Penrose in 1969, might explain how some of the most energetic jets in the universe are produced. Black holes come in different sizes, and their formation depends on their mass. Stellar black holes form when massive stars die. When a star at least 20 times heavier than our Sun runs out of fuel, its core collapses. The outer layers explode outward in a supernova, but the core keeps falling inward. If enough mass remains, roughly 3 or more solar masses, nothing can stop the collapse, and a black hole forms. These stellar black holes typically range from about 3 to 50 times the mass of our Sun. At the other extreme are supermassive black holes, the monsters that lurk at the centers of galaxies. Sagittarius A, the black hole at the heart of our Milky Way, contains about 4 million solar masses. Some supermassive black holes in other galaxies are billions of times more massive than our Sun. How these giants formed remains one of astronomy's biggest mysteries. They might have grown from smaller black holes through mergers and feeding, or they might have formed directly from the collapse of massive gas clouds in the early universe. Between these extremes are intermediate mass black holes, containing hundreds to thousands of solar masses. Evidence for their existence is mounting, though they remain elusive. In 2020, the LIGO and Virgo gravitational wave detectors observed the merger of 2 black holes that produced an intermediate mass black hole of about 142 solar masses. The first direct evidence that these middleweight objects exist. And then, there are primordial black holes, which might have formed in the first moments after the Big Bang. when the density fluctuations in the newborn universe were extreme enough to create black holes directly. These could range from microscopic, smaller than an atom, to enormous. Some scientists have proposed that primordial black holes might account for some of the mysterious dark matter that pervades the cosmos. Unlike dark matter made of exotic particles, primordial black holes would be made of ordinary matter compressed to extreme density. They would interact with other matter only through gravity, making them almost impossible to detect directly. The diversity of black holes in our universe is remarkable. We have confirmed the existence of stellar black holes in X-ray binary systems since the 1970s. We have imaged supermassive black holes directly with the Event Horizon Telescope. We have heard gravitational waves from black hole mergers. The universe, it seems, is exceptionally good at making black holes, a fact that will become important when we discuss cosmological natural selection. Now we come to one of the deepest puzzles in all of physics, the black hole information paradox. In 1974, Stephen Hawking made a startling discovery. By combining quantum mechanics with general relativity, he showed that black holes are not perfectly black. They emit a faint glow of radiation, now called Hawking radiation, and slowly evaporate over time. The mechanism is subtle. Near the event horizon, the quantum vacuum is constantly producing pairs of virtual particles. Normally, these pairs pop into existence and then annihilate each other almost instantly. But at the event horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real, carrying away a tiny bit of the black hole's energy. Over time, this drains the black hole's mass. For a stellar black hole, this process is unbelievably slow. A black hole with the mass of our sun would take about 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros, far longer than the current age of the universe. But in principle, all black holes will eventually evaporate completely. Here's the problem. When something falls into a black hole, an astronaut, a book, a cup of coffee, it carries information with it. The specific arrangement of atoms, the data encoded in the book, the thermal state of the coffee. In ordinary physics, information is never truly destroyed. You could, in principle, always run the equations backward and figure out what something was from what it became. But Hawking's calculations suggested that the radiation coming out of a black hole carries no information about what went in. It's purely thermal, perfectly random, like the glow from a hot piece of iron. This means that when the black hole finally evaporates, all the information about everything that ever fell in would simply vanish from the universe. This violates a fundamental principle of quantum mechanics. It would mean that physics is not reversible, that the past cannot be reconstructed from the present. For decades, physicists argued about whether information is truly lost in black holes. Today, most physicists believe that information is preserved somehow. The discovery of the holographic principle, which we'll explore later, suggests that information might be encoded on the event horizon. Recent breakthroughs involving something called quantum extremal surfaces have provided strong evidence that Hawking radiation does carry information, just in a very subtle and scrambled way. But the full resolution remains one of the great unsolved problems in physics. The crucial insight for our purposes is this: black holes are defined by their event horizons, one-way boundaries from which nothing can escape. Now think about our own universe. We are surrounded by a horizon too. The cosmological horizon marks the edge of the observable universe, the boundary beyond which light has not had time to reach us in the 13.8 billion years since the Big Bang. Just like a black hole's event horizon, Our cosmic horizon represents a limit on what we can see or know. If you were inside a sufficiently large black hole, you might not even notice. The curvature of space-time at the event horizon of a supermassive black hole is actually quite gentle. You could cross it without feeling anything unusual. From the inside, you would see a sky full of stars, just like we do. The horizon would always seem to be a fixed distance away, retreating as you move toward it. Does this sound familiar? We look out at our universe and see galaxies in every direction. The edge of the observable universe seems to recede at the speed of light, always just out of reach. We cannot see beyond our cosmological horizon, just as nothing inside a black hole can see beyond its event horizon. Could we be on the inside of an enormous event horizon, unaware of the larger cosmos beyond? The parallels are striking. An observer inside a sufficiently large black hole would experience local physics that looks completely normal. Gravity would pull things together. Light would travel in straight lines over short distances. Stars could form and shine. Galaxies could spin. Life could evolve. The curvature of space-time at the event horizon of a supermassive black hole is actually quite gentle, far gentler than the curvature at the surface of Earth. An astronaut falling through the horizon of a billion solar mass black hole might not even notice the crossing. From inside, the horizon would look like a distant boundary, always retreating as you approached. The geometry would be strange, but not obviously impossible. And the matter inside would have exactly the mass-to-radius ratio we observe in our universe. The comparison raises profound questions. Is our cosmic horizon just a limit on what we can see, or is it something more fundamental, an event horizon that defines the boundary of our existence? Are the galaxies we observe floating in infinite space, or are they trapped inside a gravitational structure from which nothing can escape? As we're about to see, the Big Bang Theory itself has problems that might be elegantly solved if our universe began not with a singularity, but inside a black hole. The Big Bang Theory is one of the most successful scientific theories ever developed. It explains why the universe is expanding. It predicts the existence of the cosmic microwave background radiation, that faint afterglow of the early universe that we can detect with radio telescopes. It accurately describes the abundance of light elements like hydrogen and helium that formed in the first few minutes after the Big Bang. But the theory has a dirty secret. Right at its very beginning, at the moment of creation itself, everything breaks down. According to the standard Big Bang model, our universe began about 13.8 billion years ago in a state of infinite density and infinite temperature, concentrated in an infinitely small point. This initial state is called a singularity. From this incomprehensible beginning, space itself exploded outward. Matter and energy cooled as the universe expanded. Particles formed, then atoms, then stars, then galaxies, and eventually, us. The problem is that word, infinite. In physics, infinities are almost always a sign that something has gone wrong. When your equations produce an infinity, it usually means you've pushed your theory beyond its limits, into a regime where it no longer applies. The singularity at the beginning of the Big Bang is not a triumph of the theory. It's a confession of ignorance. This problem was put on rigorous mathematical footing by Roger Penrose and Stephen Hawking in the 1960s and 1970s. Their singularity theorems proved that under very general conditions, general relativity predicts the formation of singularities. These theorems showed that singularities are not just a quirk of certain special solutions, they are an inevitable feature of the theory. Penrose's original 1965 theorem showed that once a trapped surface forms, a region where gravity has become so strong that even light rays are converging, a singularity must develop somewhere in the future. This was a theorem about black holes. Hawking then reversed the logic. He showed that if you trace the expansion of the universe backward in time, the same reasoning applies. If the universe is expanding now, it must have been denser in the past. Following this backward, the density increases without limit. Eventually, all the matter in the universe is compressed into a region of infinite density, a singularity. The Penrose-Hawking singularity theorems won Penrose a share of the Nobel Prize in Physics in 2020. They are mathematically proven, given the assumptions of general relativity. But this is precisely what makes them so troubling. They tell us that general relativity predicts its own breakdown. At the singularity, the theory produces nonsense. What does it mean to say the temperature was infinite, or that the density was infinite, or that the size was zero? These are not descriptions of physical reality. They are signs that we need a better theory, one that can describe what actually happened at the beginning of time. But the singularity isn't the only problem with the standard Big Bang model. There are at least 3 other major puzzles that have troubled cosmologists for decades. The first is called the horizon problem. Look at the cosmic microwave background, that radiation left over from when the universe was about 380,000 years old. No matter which direction you look, the temperature is almost exactly the same, about 2.725 Kelvin, with variations of only a few parts in 100,000. This uniformity is astonishing. Here's why it's a problem. Consider 2 points on opposite sides of the sky, separated by nearly 180 degrees. The light from those points has been traveling toward us for almost the entire age of the universe. But those 2 regions have never been in contact with each other. Even at the speed of light, there hasn't been enough time since the Big Bang for a signal to travel from one to the other. If 2 regions have never been in causal contact, if no information, energy, or influence could ever have passed between them, why do they have exactly the same temperature? It's like walking into 2 rooms on opposite sides of a building that have been sealed since construction, and finding them at exactly the same temperature, down to 1/100th of a degree. Without some connection between them, this would be an absurd coincidence. Yet the cosmic microwave background shows us exactly this. Regions that could never have communicated are somehow precisely coordinated. The standard Big Bang model offers no explanation. The second puzzle is the flatness problem. The geometry of the universe depends on its density. If the density is above a certain critical value, space-time curves back on itself and the universe is closed, like the surface of a sphere. If the density is below the critical value, space-time curves the opposite way and the universe is open, shaped like a saddle. And if the density equals exactly the critical value, the universe is flat. Space extends in straight lines forever. Observations show that our universe is very, very close to flat. The density is within about 1% of the critical value. This might seem unremarkable until you think about how the universe evolves. Any slight departure from perfect flatness gets magnified over time. If the early universe had been even slightly denser than critical, the expansion would have slowed and reversed, collapsing the cosmos back into a big crunch within a few years of the Big Bang. If it had been slightly less dense, the universe would have expanded so rapidly that matter would never have clumped together to form galaxies, stars, or planets. For the universe to be this close to flat today, after 13.8 billion years of expansion, it must have been incredibly close to flat at the beginning. Calculations show that at 1 second after the Big Bang, the density must have been fine-tuned to within 1 part in 10 to the power of 15. At the Planck time, 10 to the minus 43 seconds after the Big Bang, the fine-tuning must have been even more extreme. 1 part in 10 to the power of 60. Why would the universe begin with such a precisely tuned density? The standard Big Bang model doesn't say. It just accepts this as an initial condition. The third puzzle is the monopole problem. In the 1970s, particle physicists developed grand unified theories that attempted to combine 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, into a single framework. These theories predicted that in the extremely hot conditions of the early universe, exotic particles called magnetic monopoles should have been produced in enormous quantities. A magnetic monopole is like a magnet with only one pole, either north or south, but not both. Every magnet you've ever seen has both a north and south pole. If you break a bar magnet in half, you don't get a north piece and a south piece. You get 2 smaller magnets, each with both poles. This is one of the most fundamental facts about magnets. They always come in pairs. Monopoles, if they exist, would be different. They would be isolated magnetic charges, the magnetic equivalent of an electron's electric charge. And according to grand unified theories, they should be incredibly heavy, about 10 to the power of 16 times heavier than a proton, and absolutely stable. Once created, they would never decay. The calculations were alarming. The conditions in the early universe should have produced roughly 1 monopole for every 10 billion photons. Given that there are about 400 photons in every cubic centimeter of space today, most of them from the cosmic microwave background, this would mean monopoles should be almost as common as atoms. Their combined mass would be far greater than all the ordinary matter in the universe. The cosmos should be dominated by monopoles, but we have never found a single one. Despite extensive searches using particle detectors, moon rocks, ancient mica, and ocean sediments, no magnetic monopole has ever been detected. If they exist, they must be extraordinarily rare, far rarer than grand unified theories predict. Where are they? In 1980, a young physicist named Alan Guth proposed a radical solution to all 3 problems at once. His idea was called cosmic inflation. Guth proposed that in the first tiny fraction of a second after the Big Bang, around 10 to the minus 36 seconds, the universe underwent a period of extraordinarily rapid expansion. During this inflationary epoch, the universe expanded by a factor of at least 10 to the power of 26, and possibly much more, in less than 10 to the minus 32 seconds. Space itself stretched faster than the speed of light. This doesn't violate relativity, because it was space itself expanding, not anything moving through space. Inflation elegantly solves all 3 problems. The horizon problem is solved because before inflation, the entire observable universe was contained in a tiny region, small enough for light to have crossed it many times. Everything was in causal contact. Everything had time to reach the same temperature. Then inflation stretched this small, uniform region to cosmic size. The flatness problem is solved because inflation stretches any curvature to near zero. Imagine drawing a curve on a balloon and then inflating the balloon by a factor of 10 to the power of 26. No matter how curved the original line was, after that much stretching, it would appear perfectly straight. Inflation drives the universe toward flatness, regardless of its initial curvature. The monopole problem is solved because inflation dilutes any monopoles that formed before it. If you had a certain number of monopoles in a small volume and then expanded that volume by 10 to the power of 78, those monopoles would be spread so thin you might have only one in the entire observable universe, or none at all. Inflation has been spectacularly successful. its predictions for the tiny fluctuations in the cosmic microwave background have been confirmed by satellite observations with remarkable precision. But inflation has problems of its own. What drove the inflation? In most theories, it's a hypothetical quantum field called the inflaton. But we have no direct evidence that the inflaton exists. We don't know what particle it corresponds to. We don't know why it had just the right properties to cause inflation. The inflaton is, in essence, a placeholder, a name for whatever caused inflation, without any understanding of what it actually is. Why did inflation stop? The inflaton field must have somehow transitioned from a high-energy state to a low-energy state, ending the rapid expansion. This process, called reheating, supposedly converted the energy of the inflaton into the particles that make up the universe today. But the mechanism for this transition is poorly understood, and different versions of inflation theory propose radically different reheating scenarios. Why did inflation start? Before inflation, something must have set the initial conditions that allowed inflation to begin. But inflation was invented precisely to avoid needing special initial conditions. If inflation requires special conditions to begin, then we've just moved the fine-tuning problem rather than solving it. What happened before inflation? Standard inflation theories are silent on this question. They start the story at 10 to the minus 36 seconds after the beginning. But they can't tell us what happened before. The singularity is still there, lurking in the background, pushed back but not eliminated. Some physicists, including Roger Penrose, have argued that inflation doesn't really solve the fine-tuning problems. It just moves them to the properties of the inflaton field. The initial state required for inflation to work, Penrose has calculated, is actually more special and unlikely than the initial state inflation was supposed to explain. This criticism has not been widely accepted, but it highlights genuine concerns about the foundations of the theory. There are also different versions of inflation that make different predictions. Some predict a universe with small negative curvature. Others predict exactly flat. Some predict strong gravitational wave signatures. Others predict weak ones. The data from the Planck satellite has ruled out some versions, but not others. The fact that inflation theory is so flexible that it can be adjusted to fit almost any observation makes some physicists uncomfortable. A theory that can explain everything explains nothing. Despite these concerns, the inflationary paradigm remains dominant. The evidence from the cosmic microwave background is strong, but the questions inflation was meant to answer have not gone away. The singularity remains. The origin of the inflaton remains mysterious. The beginning of time remains shrouded. What if there's another solution? What if the Big Bang wasn't a singularity at all, but something else entirely? What if our universe didn't emerge from nothing, but from something, the interior of a black hole? Now we come to the strange mathematical relationship that has haunted cosmologists for half a century. The Schwarzschild radius of an object, the size it would need to be compressed to in order to form a black hole, is given by a beautifully simple formula. Rs naur 2gm_c2, where g is the gravitational constant, m is the mass, and c is the speed of light. Let's calculate the Schwarzschild radius for all the matter and energy in the observable universe. The observable universe contains roughly 10 to the power of 53 kilograms of matter. This estimate includes ordinary matter, dark matter, and the mass equivalent of dark energy. When you plug this number into the Schwarzschild formula, you get a radius of about 13.8 billion light-years. That number should stop you in your tracks. The radius of the observable universe, the distance from us to the cosmological horizon, is also about 13.8 billion light-years. This is called the Hubble radius, roughly the distance light has traveled since the Big Bang. The Schwarzschild radius of all the mass in the universe and the actual radius of the observable universe are essentially the same number. This is not a small coincidence. This is not a factor of 2 coincidence. The two numbers match to within the precision of our measurements. Let's think about what this means. If you took all the matter and energy in the observable universe and calculated how much space a black hole of that mass would occupy, you would get a black hole exactly the size of the observable universe. We are inside a sphere whose mass-to-radius ratio is exactly what you would expect for the interior of a black hole. As the physicist Michio Kaku has put it, if you want to know what it looks like inside a black hole, look around. This relationship was noticed decades ago, but for a long time it was dismissed as a coincidence. The physicist Sean Carroll, among others, has argued that it follows automatically from having a spatially flat universe. The critical density, the density needed for the universe to be flat, combined with the Hubble radius through the Friedmann equations, naturally produces this relationship. Here's the argument. The critical density of the universe is given by RCRite 3H2 8pg, where h is the Hubble constant, describing the expansion rate. If you multiply this density by the volume of the observable universe, a sphere of radius c/h, you get a total mass, and the Schwarzschild radius of that mass turns out to equal ch, the Hubble radius. So Carroll argues, this isn't really a coincidence at all. It's a mathematical consequence of living in a flat universe. But this explanation just pushes the mystery back a step. Why is the universe flat? As we discussed earlier, the flatness of the universe is itself a puzzle. The density had to be tuned to extraordinary precision at the beginning. Inflation is supposed to explain this, but inflation has its own problems. And there's something philosophically unsettling about dismissing this relationship as a mere consequence of flatness. If you live inside a structure whose size and mass exactly match the formula for a black hole, perhaps the most natural explanation is that you live inside a black hole. Different physicists have very different intuitions about this coincidence. Some see it as deeply significant, a clue pointing toward a fundamental truth about the universe. Others see it as an artifact of definitions and equations, nothing more. The astrophysicist John Wheeler, who coined the term black hole and mentored generations of physicists including Kip Thorne and Richard Feynman, was fascinated by this relationship. He saw it as evidence of a deep connection between cosmology and black hole physics. The universe, he once mused, is built on a plan the profound symmetry of which is somehow present in the inner structure of our intellect. The physicist Paul Davies has written extensively about this coincidence, noting that it appears to be more than just mathematics. If the universe is spatially flat, Davies observed, then the total energy of the universe is zero. The negative gravitational energy exactly balances the positive matter energy. This is precisely what you would expect if the universe emerged from nothing. On the other side, Sean Carroll has argued forcefully that the coincidence is explained by flatness and nothing more. The universe has critical density because it's flat, Carroll has written, and it's flat because of inflation. There's no deeper mystery here, just the natural consequences of our cosmological model. But even Carroll acknowledges that this pushes the question back. Why is the universe flat? Why did inflation happen in just the right way to make it flat? The fine-tuning has not disappeared. It has only moved. In 1972, the physicist Raj Pathria took the relationship seriously. In a paper published in Nature, he compared the mathematics of a closed universe with the mathematics of the region inside a black hole. He found that the two descriptions could be made to match. Our universe, he suggested, might be the interior of a black hole located in some larger space. Pathria's idea was ahead of its time. The paper was intriguing, but incomplete. It couldn't explain why the universe was expanding rather than collapsing, or how it got started. The idea sat dormant for decades. But the coincidence kept nagging at people, and in the 1990s, a related discovery added new fuel to the fire: the holographic principle. In ordinary physics, information scales with volume. If you have a box of gas, the amount of information needed to describe all the particles doubles when you double the volume. This seems obvious. More space means more stuff, which means more information. But in 1972, Jacob Bekenstein made a startling discovery about black holes. He showed that the entropy of a black hole, a measure of its information content, is proportional not to its volume, but to the area of its event horizon. A black hole with twice the surface area has twice the entropy, regardless of the volume enclosed. This is bizarre. It suggests that everything that happens inside a black hole, all the matter that falls in, all the information it carries, is somehow encoded on the two-dimensional surface of the event horizon. The interior is an illusion, or at least a redundant description. Gerard 't Hooft and Leonard Susskind developed this insight into a principle, the holographic principle. They proposed that any region of space can be completely described by information on its boundary. The maximum information content of any volume scales with its surface area, not its volume. If this is true for black holes, might it be true for the universe as a whole? The cosmological horizon around us has an area. If the holographic principle applies to the cosmos, then all the information in the observable universe, every particle, every field, every bit of data, might be encoded on that two-dimensional surface. And if the observable universe's horizon behaves like a black hole's event horizon, that's another clue that we might be inside one. The connection between mass, radius, and information suggests something profound. The universe we see around us, the three-dimensional space filled with galaxies and stars and planets, might be a kind of projection, a hologram emanating from the cosmic horizon. This sounds like science fiction, but it has become a serious area of research. The AD-CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete mathematical example of how a theory with gravity in a higher dimensional space can be exactly equivalent to a theory without gravity in a lower dimensional space. The higher dimensional physics is encoded holographically on the boundary. We don't yet know if our universe works this way. The AD-CFT correspondence applies to universes with different geometries than ours. But the fact that such holographic dualities exist at all suggests that the holographic principle may be a deep truth about reality. And if we're living in a holographic universe whose boundary is its cosmological horizon, and that horizon has exactly the properties of a black hole event horizon, then perhaps the simplest explanation is the most radical one. We really are inside a black hole. In 2010, a Polish-American physicist named Nikodem Popławski published a series of papers that changed the conversation about black hole cosmology. Working at Indiana University, Popławski showed how universes could actually form inside black holes, and he did it using a theory that had been sitting on the shelf, mostly ignored, for decades. The theory is called Einstein-Cartan-Siama-Kibble gravity, or ECSK for short. It's a natural extension of Einstein's general relativity that includes something Einstein's original theory left out: the intrinsic spin of matter, Every particle of matter has spin. Electrons, quarks, neutrinos, they all carry an intrinsic angular momentum, a kind of built-in rotation. In ordinary circumstances, this spin has almost no effect on gravity. But in extreme conditions, when matter is compressed to unimaginable densities, spin changes everything. In the ECSK theory, the spin of particles couples to a property of spacetime called torsion. Torsion is like curvature's cousin. While curvature describes how spacetime bends, torsion describes how it twists. In Einstein's original theory, torsion was assumed to be zero. But there's no fundamental reason for this assumption. It was a simplification. When torsion is included, the equations of gravity change, and the change becomes dramatic at extremely high densities, densities that exist inside black holes. To understand torsion, think about what happens when you walk on a curved surface versus a twisted one. If you're walking on a sphere, the surface curves but doesn't twist. Parallel lines eventually meet, but they don't spiral. Torsion is different. It's like walking on a surface that's not just curved, but also twisted, like a spiral staircase. In spacetime, torsion means that parallel lines don't just converge or diverge, they rotate around each other. In everyday physics, torsion is completely negligible. The spin of particles is too small and the densities are too low for it to have any measurable effect. You could live your entire life, and physicists have done their entire careers, without ever encountering a situation where torsion matters. But inside a collapsing star, as matter is compressed toward the density of nuclear matter and beyond, things change. At densities exceeding 10 to the power of 18 kilograms per cubic meter, far denser than atomic nuclei, the cumulative effect of all those spinning fermions produces significant torsion. And this torsion acts like a repulsive force. The mathematics shows that the repulsion grows rapidly as density increases. It's negligible at nuclear densities, but becomes enormous at densities around 10 to the power of 50 kilograms per cubic meter. At such extreme conditions, the torsion-induced repulsion overwhelms gravity. Here's what happens according to Popławski's analysis. Imagine a massive star at the end of its life, collapsing to form a black hole. Matter falls inward, compressed by the enormous gravity. Density increases. An event horizon forms. In standard general relativity, the collapse continues without limit. Matter crushes down and down, density grows without bound, and a singularity forms, a point of infinite density where the laws of physics break down. But in ECSK gravity, something different happens. As the density approaches the level of nuclear matter and then exceeds it, the torsion produced by the spin of fermions becomes significant, and this torsion generates a repulsive force. The repulsion is negligible at ordinary densities. You would never notice it in everyday life, or even in a neutron star. But when matter is squeezed to densities far beyond anything we can create in laboratories, the repulsive effect becomes enormous. It pushes back against the gravitational collapse. The collapse doesn't continue to infinity. Instead, it stops. The matter reaches a maximum density, incredibly high, but finite, and then bounces. This bounce is not a gentle rebound. It's a violent explosion. The matter that was falling inward suddenly rushes outward at tremendous speed. Space itself begins to expand. But here's the crucial point. This expansion happens on the other side of the event horizon. To observers in the original universe, nothing unusual appears to happen. They see the black hole form, and it looks like any other black hole. The expansion is hidden behind the horizon. On the inside, however, a new universe is being born. the collapsing matter bounces and begins expanding into what Popławski calls a new branch of space-time. This expanding region has all the characteristics of a Big Bang: extreme density, high temperature, rapid expansion, but without the impossible singularity. The Big Bang is replaced by a big bounce. This scenario has a remarkable consequence. It naturally produces cosmic inflation. In the standard Big Bang model, inflation has to be added as a separate mechanism. A hypothetical inflaton field is invoked to drive a brief period of exponential expansion. This requires new physics beyond the standard model, and the inflaton has never been observed. In Popławski's model, inflation comes free. The repulsive force generated by torsion causes the rapid expansion automatically. No new fields are needed. No new parameters must be fine-tuned. The same physics that prevents the singularity also drives inflation. Popławski's work provides a physical mechanism for the black hole cosmology that earlier thinkers like Patria could only sketch. It explains how a universe can form inside a black hole. It explains why the Big Bang looks like a Big Bang. It explains why inflation happened. And it makes a testable prediction. If our universe formed inside a black hole that was rotating, and virtually all black holes rotate, then our universe should have inherited some of that rotation. A rotating black hole has angular momentum, and when matter bounces and expands inside it, some of that angular momentum should be transferred to the new universe. The baby universe would be born spinning. This is a remarkable prediction because the standard Big Bang model assumes the universe is not rotating. The cosmological principle, the assumption that the universe looks the same in all directions, implies no preferred axis of rotation. If the universe were spinning, distant galaxies on opposite sides of the sky should show systematic differences in their redshifts, as one side moves toward us and the other moves away. For decades, observations seem to confirm that the universe is not rotating. The cosmic microwave background is extraordinarily uniform. There is no obvious axis of rotation visible in the distribution of galaxies, but there have always been anomalies. The CMB shows unexpected features, a cold spot, alignments that shouldn't exist if the universe is perfectly uniform. What cosmologists have called the axis of evil. These could be statistical flukes, or they could be hints of something deeper. We'll return to this prediction later because in 2025, observations from the James Webb Space Telescope may have provided the first evidence that our universe is indeed rotating, exactly as Popławski's model predicts. The Einstein-Cartan theory isn't new physics invented to explain the universe. It's a natural extension of general relativity that was first proposed by Élie Cartan in the 1920s and further developed by Dennis Sciama and Thomas Kibble in the 1960s. It has been mathematically well understood for decades. Popławski's contribution was to work out its consequences for gravitational collapse and cosmology, and to recognize that it provides a natural solution to the singularity problem. In this picture, our universe is the interior of a black hole that formed in a larger parent universe. The Big Bang was not the beginning of everything. It was a transformation, a bounce, a rebirth. Time did not start at the singularity because there was no singularity. Before the bounce, there was the collapse. Before the collapse, there was the parent universe, and every black hole in our universe might contain another baby universe on the other side. In 1992, a theoretical physicist named Lee Smolin proposed one of the most audacious ideas in the history of cosmology. He asked, "What if universes evolve?" Smolin, who would later become a professor at the Perimeter Institute in Canada, was troubled by the fine-tuning problem. The physical constants of our universe, The mass of the electron, the strength of gravity, the charge of the proton seem bizarrely well suited for the existence of stars, planets, and life. If many of these constants were even slightly different, the universe would be sterile. The traditional response to this puzzle is the anthropic principle. We observe a life-friendly universe because we couldn't exist to observe any other kind. But Smolin found this unsatisfying. It explains nothing. It makes no predictions. It's a philosophical shrug, not a scientific theory. Smolin proposed an alternative: cosmological natural selection. The idea is simple and profound. Suppose, as Popowski would later work out in detail, that black holes give rise to new universes. When a black hole forms, a baby universe is born on the other side of the event horizon, beyond the reach of the parent. Now suppose that the physical constants in the baby universe are not exactly the same as in the parent. They're similar. Mutations are small, but not identical. Perhaps the mass of the electron is slightly different, or the strength of the strong nuclear force is tweaked by a tiny amount. If this is true, then universes reproduce. Each universe gives rise to as many offspring as it has black holes. And if the physical constants vary slightly from generation to generation, then a kind of natural selection operates. Some combinations of physical constants are better at producing black holes than others. A universe where stars form easily and massive stars are common will produce lots of black holes. A universe where nuclear fusion is impossible, or where gravity is too weak for stars to ignite, will produce few or no black holes. Over countless generations, and there could be more generations than there are atoms in our universe, the multiverse becomes dominated by universes with parameters that maximize black hole production. This has a stunning implication. We shouldn't be surprised that our universe has physical constants that allow for stars and complex chemistry. Universes that can make stars can make black holes. Universes that can make black holes have more offspring. Over many generations, star-friendly, life-friendly parameters are selected for. Think about what this means. In our universe, stars burn hydrogen through nuclear fusion. This requires the strong nuclear force to be just right, strong enough to bind protons and neutrons together, but not so strong that all hydrogen gets fused into heavier elements in the first few minutes after the Big Bang. The mass difference between neutrons and protons has to be just right. If neutrons were too heavy, they would all decay before stars could form. If they were too light, all the protons would become neutrons, and you couldn't have chemistry. These constraints might seem like cosmic good luck, but in cosmological natural selection, they're the result of selection pressure. Universes where the strong force is too weak don't form stable nuclei, so they don't form stars, so they don't form many black holes, so they don't have many offspring. Universes where the strong force is too strong fuse all their hydrogen into iron immediately, leaving nothing to power stars. So again, few black holes, few offspring. Only universes with parameters in a narrow range can produce abundant black holes. And producing abundant black holes also requires producing abundant stars. And producing abundant stars also produces the conditions for planets and life. It's not that the universe was designed for life, it's that the same parameters that make universes good at reproducing, lots of black holes, also happen to make them good at hosting life. Life is a side effect of cosmic fertility. This is a completely different kind of explanation than the anthropic principle. It doesn't just say, things are this way because we're here to see them. It says, things are this way because of a physical process that favors certain outcomes. It takes the mystery of fine-tuning and transforms it into a question about dynamics and selection. And unlike the anthropic principle, cosmological natural selection makes testable predictions. It's science, not philosophy. When Smolin published the theory in 1992, he proposed a specific test. If the universe has been selected to maximize black hole production, then tweaking any physical parameter should reduce the number of black holes. The universe should be at a local maximum. One key parameter is the mass limit for neutron stars. Neutron stars are the collapsed cores of massive stars that weren't quite massive enough to form black holes. Above a certain mass, the Tolman-Oppenheimer-Volkoff limit, even neutron star matter cannot resist gravity, and the star collapses into a black hole. Smolin originally predicted that this limit should be about 1.6 solar masses. If it were higher, fewer black holes would form. If the prediction failed, if we found neutron stars significantly heavier than this, it would suggest the universe is not optimized for black hole production. In 2010, astronomers discovered a neutron star with a mass of 1.97 solar masses. In 2019, another was found at 2.08 solar masses. These observations initially seemed to challenge Smolin's prediction, but the situation is more subtle. Nuclear astrophysicists have revised their models, and some versions of the theory can accommodate these heavier neutron stars. The question of whether the universe truly maximizes black hole production remains open. The theory attracted strong criticism from some quarters. The string theorist Leonard Susskind, in particular, challenged Smolin on several fronts. One objection concerns information. In recent decades, physicists have increasingly concluded that information cannot be destroyed, not even by falling into a black hole. Hawking radiation, it turns out, carries information back out. The black hole information paradox, which seemed to show that information was lost forever, appears to be resolved. Information is scrambled, encoded in subtle correlations in the radiation, but not destroyed. If that's true, how can information about physical constants pass from a parent universe into a baby universe through a black hole? The black hole shouldn't allow information to cross its event horizon in either direction. The parent universe's physics should be completely isolated from the child's. This is the substance of the famous Smolin-Susskind debate, which played out in exchanges on the Edge website and in various publications through the early 2000s. Susskind argued that the very feature of black holes that makes them interesting, their ability to hide information behind an event horizon, also makes cosmological natural selection impossible. If information can't escape a black hole, how can the genetic information of physical constants be transmitted to offspring universes? Susskind's critique cut deep. He wasn't arguing that universes can't form in black holes. That's a separate question. He was arguing that even if they do, there can be no inheritance. Without inheritance, there is no selection. Without selection, there is no explanation for fine-tuning. Smolin's response was characteristically subtle. He pointed out that Darwin proposed natural selection without understanding the mechanism of heredity. Darwin knew nothing of DNA, nothing of genes, nothing of the molecular biology that would later explain how traits are passed from parent to offspring. Gregor Mendel's work on genetics was ignored for decades. The modern synthesis that combined Darwin's theory with Mendelian genetics didn't emerge until the 1930s and 1940s. The power of Darwin's theory was that it identified the pattern, reproduction with variation and selection, without needing to specify the molecular details. The mechanism was unknown, but the logic was sound, and history vindicated Darwin. The mechanism was eventually discovered, and it worked exactly as the theory required. Similarly, Smolin argues, cosmological natural selection identifies a pattern that could explain fine-tuning, the exact mechanism by which physical constants are passed from parent to child universe. The genetics of the multiverse may require physics we don't yet understand. Perhaps quantum gravity allows for information transfer in ways that classical black hole physics forbids. Perhaps the process happens during the bounce, when the classical description breaks down. Perhaps there's something about torsion and the Einstein-Cartan theory that changes the picture. That doesn't mean the pattern is wrong. It means the mechanism is unknown, just as Darwin's mechanism was unknown in 1859. It's a bold response. Some find it compelling, others find it too speculative. The debate continues. What's remarkable is that cosmological natural selection predicted, before Popowski's work, that black holes should create new universes. Smolin arrived at this idea through theoretical reasoning about fine-tuning and evolution. Popowski arrived at it through careful analysis of the Einstein-Cartan equations. That two very different approaches converge on the same picture is striking. The theory remains controversial. Many physicists view it as too speculative to take seriously. Others see it as one of the few genuinely explanatory frameworks for the fine-tuning problem. What everyone agrees is that if universes really do reproduce through black holes, and if physical constants really do vary slightly from generation to generation, then natural selection would inevitably operate. The logic is impeccable. The question is whether the premises are true. As Smolin himself has noted, the best way to test the theory is to look for evidence that our universe came from a black hole, evidence that it has properties you would expect the interior of a black hole to have. Properties like, say, a rotating frame of reference, or a cosmic horizon that behaves like an event horizon, or a mass-to-radius ratio that matches the Schwarzschild formula. All of which brings us back to the strange mathematical coincidence with which we started. In 1972, Jacob Bekenstein, a young physicist who had recently completed his PhD at Princeton, made a discovery that would transform our understanding of the universe. He was studying black holes, and he noticed something strange about their entropy. Entropy is a measure of disorder, or equivalently, of the number of possible arrangements of a system. A gas in a box has high entropy because its molecules can be arranged in countless ways. A crystal has low entropy because its atoms are locked in a regular pattern. In ordinary systems, entropy scales with volume. A box twice as big can hold twice as much gas, with twice as many possible arrangements and twice as much entropy. But black holes are different. Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. A black hole with twice the surface area has twice the entropy. The volume enclosed is irrelevant. This was puzzling. Why should a three-dimensional object have its information content determined by its two-dimensional surface? The formula Bekenstein discovered was remarkable. S, Ka4L2, where S is the entropy, K is Boltzmann's constant, A is the area of the event horizon, and L is the Planck length, the smallest meaningful length in physics, about 10 to the minus 35 meters. This formula tells us that the maximum information that can be contained in any region of space is finite, and it's determined by the boundary of that region, not its interior. Bekenstein's work was initially controversial. Stephen Hawking argued against it, pointing out that if black holes have entropy, they must also have temperature. But classical black holes absorb everything and emit nothing, which would make their temperature absolute zero. This is what led Hawking, in 1974, to his famous calculation showing that black holes do emit radiation. Hawking radiation confirmed Bekenstein's insight. Black holes really do have temperature and entropy. And the entropy really does scale with surface area. In the early 1990s, Gerard 't Hooft and Leonard Susskind took Bekenstein's result and pushed it further. If the maximum information in any region is determined by its boundary area, then perhaps the boundary contains all the information there is. Perhaps the three-dimensional interior is somehow redundant, a projection from the two-dimensional surface. They called this the holographic principle, named after holograms, those shimmering images that encode three-dimensional information on a two-dimensional surface. The holographic principle proposes that our three-dimensional reality is a kind of hologram. Everything we see, touch, and experience is encoded on a distant two-dimensional surface. The apparent depth of space is an illusion, or at least it's a derived property, not fundamental. This sounds like mysticism, but it's based on hard mathematics. In 1997, the Argentine physicist Juan Maldacena provided the most concrete evidence for the holographic principle. Working with string theory, he showed that a certain kind of universe with gravity, a five-dimensional space with negative curvature called anti-de Sitter space, is exactly equivalent to a four-dimensional quantum field theory without gravity living on its boundary. This is called the ADS-CFT correspondence. The ADS stands for anti-de Sitter, the curved space with gravity. The CFT stands for conformal field theory, the theory on the boundary. Maldacena proved that these two very different-looking theories are actually the same theory in disguise. Every calculation you can do in one has a corresponding calculation in the other. This was a stunning result. Imagine discovering that a dictionary in one language is exactly equivalent to a physics textbook in another language, that every word in the dictionary corresponds to a physical fact in the textbook, and vice versa. The two documents look nothing alike, but they contain identical information. That's what Maldacena found. A theory describing gravity and matter in five-dimensional curved space is identical to a theory describing quantum particles in four-dimensional flat space with no gravity at all. The gravitational physics of the bulk is perfectly encoded in the quantum physics of the boundary. It showed that holography isn't just a vague principle. It's a precise mathematical duality. Gravity in the bulk is equivalent to quantum mechanics on the boundary. The interior is encoded on the surface. Maldacena's paper became the most cited paper in the history of high-energy physics, with over 20,000 citations. It launched a new field of research and provided a powerful tool for understanding quantum gravity. String theorists, quantum field theorists, and even condensed matter physicists have used ADS-CFT to solve problems that seemed intractable before. Now, our universe is not an anti-de Sitter space. Our universe has positive curvature, or at least it's not negatively curved in the way ADS is, so the ADS-CFT correspondence doesn't apply directly to us. But the success of holography in this controlled setting suggests that something like it might be true more generally. The principle that information scales with area rather than volume and that bulk physics can be encoded on boundaries may be a deep truth about quantum gravity, and this connects directly to the black hole universe hypothesis. If our universe is the interior of a black hole, then our cosmological horizon, the boundary of the observable universe, is analogous to an event horizon. And if the holographic principle holds, all the information in our observable universe might be encoded on that horizon. The three-dimensional space we live in, the galaxies we see, the stars and planets and people, all of it might be a holographic projection from the cosmic horizon. We would be living inside a hologram, contained within a black hole, itself contained within a larger universe. This picture has helped resolve one of the deepest puzzles in physics, the black hole information paradox. When something falls into a black hole, where does its information go? Hawking originally thought it was destroyed, but this violates quantum mechanics. The holographic principle suggests an answer. The information is encoded on the event horizon. It's not lost, it's just stored in a different form on a two-dimensional surface. Recent work on quantum extremal surfaces and the page curve has shown, using the tools of holography, that information really does come back out in Hawking radiation, just scrambled almost beyond recognition. The page curve, named after physicist Don Page, describes how the entropy of Hawking radiation should change over time if information is preserved. For decades, Hawking's calculations predicted a different curve, one that showed entropy only increasing, never decreasing, indicating permanent information loss. In 2019 and 2020, a series of breakthrough papers showed that when quantum effects are properly included, the page curve emerges naturally. The calculations are technical, involving something called the quantum extremal surface, a generalization of the event horizon that accounts for quantum entanglement. But the conclusion is clear. Black holes do preserve information exactly as the holographic principle suggests. The resolution involves a strange phenomenon called the island formula. As a black hole evaporates, certain regions of space-time that seem to be inside the black hole are actually, from an information perspective, part of the outside radiation. These islands are where the information that seemed to be lost was hiding all along. This is not mere speculation. The calculations have been done, the papers have been published, and the results have been replicated. The black hole information paradox, which tortured physicists for nearly 50 years, appears to be solved, and holography was the key. If the same logic applies to our cosmological horizon, then all the information in our observable universe is encoded on its boundary. The interior of the universe, all of it, is a holographic projection. What does this mean for reality? At one level, nothing changes. The laws of physics work the same way whether space is fundamental or holographic. The experiences we have, the observations we make, the science we do, none of it is diminished by learning that reality might have fewer dimensions than we thought. The table you're sitting at is still solid. The stars are still distant. Physics still works. But at a deeper level, holography suggests that our intuitions about space are wrong. We think of space as a container, a stage on which physics plays out. We think of it as fundamental, the most basic backdrop against which everything else happens. Holography suggests that space is emergent. It arises from something more fundamental, from information encoded on boundaries. This is a radical idea. It means that the three dimensions we perceive are not the true structure of reality. They're a kind of user interface, a way of organizing information that makes it easier to process. The real reality, if we can even call it that, is two-dimensional. Some physicists have compared this to a flight simulator. The pilot sees a three-dimensional world outside the cockpit window: mountains, cities, clouds. But that world is generated by a two-dimensional screen. The depth is constructed, not fundamental. If holography is right, then all of reality is like that flight simulator, and we are the pilot who has forgotten we're in a simulation. This connects to the idea that our universe might be inside a black hole. black holes are defined by their horizons. Our universe is defined by its horizon. If both horizons are holographic screens encoding the information of their interiors, then there's a deep unity between black hole physics and cosmology. The event horizon of a black hole encodes everything inside it. The cosmological horizon of our universe might encode everything we see. We are, perhaps, information projected onto the inner surface of a cosmic sphere. The black hole universe hypothesis and the holographic principle are two sides of the same coin, two ways of saying that reality is stranger, more subtle, and more beautiful than we ever imagined. And there's another implication. If the information in our universe is encoded on its boundary, and if that boundary is the horizon of a black hole in a parent universe, then in some sense we are information in that parent universe. The parent sees only a black hole, dark and featureless from the outside, but encoded on its surface is everything we are, every galaxy, every star, every person, every thought. We are patterns in the information on a two-dimensional surface, living out our lives in the holographic interior. This is not mysticism, it's physics. It's where the mathematics leads when you take black holes and quantum mechanics seriously. Whether it's ultimately true remains to be seen, but the journey from Bekenstein's observation about black hole entropy to this cosmic picture has been one of the most remarkable intellectual adventures in the history of science. In early 2025, a computer scientist at Kansas State University pointed his algorithms at some of the most distant galaxies ever photographed. What he found might be the most puzzling observation of the deep universe yet made, and it has profound implications for whether we live inside a black hole. Lior Shamir had spent years developing software that could automatically determine which direction a spiral galaxy rotates. Look at a spiral galaxy, and you'll see arms curving outward from the center. Follow those arms, and you can tell whether the galaxy spins clockwise or counterclockwise. For most galaxies, this is straightforward enough that even a human eye can see it. But Shamir wanted to analyze thousands of galaxies at once, far more than any human could classify by hand. He turned his attention to the James Webb Space Telescope, Advanced Deep Extragalactic Survey, known as JDES. This is one of the deepest views into the universe ever captured, revealing galaxies so distant that their light has traveled for more than 13 billion years to reach us. These are galaxies from the early universe, cosmic infants compared to our own Milky Way. In the JDES field, Shamir identified 263 spiral galaxies with clear enough structure to determine their rotation direction. And that's when something strange emerged from the data. About 2/3 of these galaxies rotate clockwise, only 1/3 rotate counterclockwise. This should not happen. In a universe governed by the cosmological principle, the bedrock assumption of modern cosmology, that the cosmos looks the same in all directions, galaxies should have no preferred spin. They form from clouds of gas that collapse under gravity, and the direction of that collapse should be random. Some would spin clockwise, some counterclockwise, but on average the numbers should balance. The asymmetry Shamir found is not subtle. You don't need sophisticated statistical analysis to see it. Look at the images yourself. 158 galaxies spinning one way, only 105 spinning the other. The chance of this happening randomly is about 1 in 500. Not impossible, but suspicious enough to demand an explanation. Think about flipping a coin. If you flip a fair coin 263 times, you'd expect roughly half heads and half tails. Getting 2/3 heads would be suspicious. Getting that result from galaxies scattered across billions of light years of space is more than suspicious. It's bizarre. The universe, according to everything we believe about cosmology, should be isotropic. That's a technical term, meaning it looks the same in all directions. There should be no preferred direction in space, no up or down, no special orientation. Galaxies should spin clockwise and counterclockwise in equal numbers, just as coin flips should come up heads and tails equally often. But they don't, at least not in the Jade's field. The clockwise bias is so strong that you don't need Shamir's computer algorithms to see it. As he put it, the difference is so obvious that any person looking at the image can see it. There is no need for special skills or knowledge to see that the numbers are different. With the power of the James Webb Space Telescope, anyone can see it. This wasn't the first hint that something might be asymmetric about our universe. Shamir had been documenting galaxy rotation asymmetries for years using ground-based telescopes. The Sloan Digital Sky Survey and Pan-STARRS had both shown similar patterns, with more galaxies rotating one direction than the other in certain parts of the sky. The effect was subtle but persistent, and it got stronger as you looked at more distant galaxies. The JWST, with its unprecedented ability to image the distant universe in sharp detail, amplified this effect dramatically. Whatever was causing it became impossible to ignore. Shamir proposed two possible explanations. The first is that the universe was born rotating. If our universe inherited angular momentum from some prior state, perhaps from the black hole that created it, if black hole cosmology is correct, then we might expect a preferred rotation direction throughout the cosmos. Every black hole we know of rotates. Angular momentum is conserved in physics. It can't simply disappear. If our Big Bang was really a big bounce inside a spinning black hole, our universe would have been born with a cosmic axis, a preferred direction built into its very fabric. To understand why this matters, think about what happens when you drain a bathtub. The water spirals as it goes down the drain, and the direction of that spiral depends on the angular momentum of the water before you pulled the plug. A universe born from a rotating collapse would work the same way. The spin would be imprinted on everything that formed within it. In our universe, all black holes rotate. Astronomers measure this spin using a parameter called the spin parameter, which ranges from 0, not spinning, to 1, spinning as fast as physics allows. Every black hole we've measured has significant spin. Sagittarius A, the supermassive black hole at the center of our galaxy, spins at about 0.9, nearly the maximum possible speed. The black holes we've detected through gravitational waves are often spinning rapidly too. This suggests that angular momentum is a fundamental property of gravitational collapse. When matter falls inward under its own gravity, it doesn't fall perfectly straight. Slight asymmetries cause it to spiral, and conservation of angular momentum means that spiral gets faster and faster as the matter compresses. The result is a spinning black hole. If our universe is inside such a black hole, it would have inherited that spin. This explanation agrees with theories such as black hole cosmology, Shamir noted, which postulates that the entire universe is the interior of a black hole. Nikodem Popławski, the physicist whose torsion-based model we explored earlier, was excited by the finding. A preferred axis in our universe, inherited from the axis of rotation of its parent black hole, might have influenced the rotation dynamics of galaxies, creating the observed clockwise-counterclockwise asymmetry, he told reporters. The discovery by the JWST that galaxies rotate in a preferred direction would support the theory of black holes creating new universes, and I would be extremely excited if these findings are confirmed. The second explanation is less dramatic but perhaps more likely. an observational bias caused by our own motion through space. The Earth orbits the Sun. The Sun orbits the center of the Milky Way, and the Milky Way itself rotates, carrying us along at about 230 kilometers per second. All this motion affects how we see distant objects through something called the Doppler shift. You've experienced the Doppler shift with sound. An ambulance siren sounds higher pitched when it's approaching and lower pitched when it's moving away. The same thing happens with light. Objects moving toward us appear slightly bluer. Objects moving away appear slightly redder. And crucially for Shamir's study, objects can appear slightly brighter or dimmer depending on their relative motion. Galaxies that rotate opposite to our direction of motion would have their approaching edge appear brighter than their receding edge. This asymmetry in brightness could make it easier for telescopes to identify and classify these galaxies, creating an artificial excess in the data. If this second explanation is correct, it would still be scientifically important. It would mean that astronomers have been underestimating the effect of our galaxy's rotation on their observations of the distant universe. As Shamir noted, if that is indeed the case, we will need to recalibrate our distance measurements for the deep universe. This recalibration could help explain other cosmic puzzles, including the Hubble tension, the mysterious discrepancy between different measurements of how fast the universe is expanding, and the seemingly impossible existence of mature galaxies at very high redshifts. But here's the tantalizing possibility. What if both explanations are partially true? What if there is a genuine cosmic asymmetry, even if our observational methods have exaggerated its apparent strength? This wouldn't be the first time astronomers have noticed something odd about the cosmic microwave background, the oldest light in the universe. Back in the early 2000s, when the WMAP satellite was mapping this primordial glow in unprecedented detail, researchers noticed something strange. The temperature fluctuations in the microwave background weren't randomly distributed across the sky. They seemed to align along a particular axis, an axis that happened to coincide with the plane of our solar system. Cosmologists nicknamed this the axis of evil, partly as a joke about the political terminology of the time, but partly out of genuine dismay. The cosmological principle, the assumption that the universe looks the same in all directions, is the foundation of modern cosmology. An axis of evil would undermine that foundation. The axis shows up in what cosmologists call the low multipoles of the CMB, the large-scale patterns of temperature variation that span huge portions of the sky. Specifically, the quadrupole and octupole modes, which describe how temperature varies at the largest angular scales, are aligned with each other to a degree that seems statistically improbable. The probability of this alignment happening by random chance in a universe that's truly isotropic is estimated at somewhere between 1 in 1,000 and 1 in 100. Not impossible, but unlikely enough to demand investigation. When the Planck satellite produced even more detailed maps of the cosmic microwave background a decade later, the axis was still there. For a long time, part of the community was hoping that this would go away, but it hasn't, said physicist Dominic Schwartz of the University of Bielefeld in Germany. The Planck data was crucial because it ruled out one of the most obvious explanations: instrumental error. WMAP and Planck were completely different satellites with different designs, different detectors, and different orbits. If both of them saw the same alignment, it couldn't be a quirk of one particular instrument. That left three possibilities. The alignment is a statistical fluke. We got unlucky in our particular realization of the cosmic microwave background. It's caused by some local astrophysical effect, something in our solar system or nearby space is contaminating the data, or it's a genuine cosmic feature. The universe really does have a preferred direction. Most cosmologists still believe the axis of evil is probably a statistical fluke or an artifact of how the data was processed. The significance of the effect hovers around 2 to 3 sigma, suggestive but not conclusive. And there are plausible explanations involving local structures and observational biases. There's also a mysterious feature called the CMB cold spot, an unusually cold region in the cosmic microwave background that's larger than what standard cosmological models predict. Some physicists have speculated that it could be the mark of a collision with another universe, though more mundane explanations involving giant cosmic voids remain possible. But combine the axis of evil with Shamir's galaxy rotation data, and a pattern begins to emerge. Maybe the universe isn't quite as isotropic as we thought. Maybe there is a subtle preferred direction, a cosmic arrow pointing somewhere. If our universe is inside a rotating black hole, this would make perfect sense. The spin axis of the parent black hole would become the preferred axis of the baby universe. Galaxies forming in this rotating space-time would preferentially spin in alignment with that cosmic axis, creating exactly the kind of asymmetry Shamir has documented. We should be careful here. One study of 263 galaxies, however striking, doesn't overturn cosmology. Shamir himself is cautious about jumping to conclusions. There could be systematic errors in the analysis. The JD's field might not be representative of the whole sky. Future observations with different telescopes in different parts of the sky will test whether the effect is real and universal. But if it is real, if the deep universe really does have a preferred rotation direction, it would be among the most profound discoveries in the history of science. It would mean our universe has an orientation, an axis, a sense of up and down written into the structure of space-time itself. And the most natural explanation for such an axis would be that our universe inherited it from the black hole that gave it birth. In May 2025, a team of physicists led by Enrique Gastañaga at the University of Portsmouth published a paper in Physical Review D that approached the black hole universe hypothesis from a completely new direction. Instead of starting with the expanding universe and asking how it began, they asked a different question entirely. What happens when a massive cloud of matter collapses under its own gravity? This might seem like a strange way to understand the origin of the universe, but Gastañaga's insight was that gravitational collapse and cosmic expansion might be two sides of the same coin. We've been looking outward, he explained. We decided to look inward instead. The standard Big Bang model asks, what happened after the initial explosion? How did matter and energy spread out to form the universe we see today? These are important questions, and the Big Bang model answers them well, but it leaves the initial moment mysterious. What was the Big Bang itself? What caused it? Why was there a singularity to begin with? Gastañaga's approach flips the question. Instead of asking what came after the beginning, he asks what physical process could have created the beginning in the first place. And gravitational collapse, the process we know creates black holes, is a natural candidate. We already know what gravitational collapse does. We've observed it happening when massive stars die. We've detected the gravitational waves rippling through space when black holes merge. We understand the physics well enough to make precise predictions about what should happen. What we haven't fully understood is what happens at the end of the collapse, after the event horizon forms. General relativity predicts a singularity, but general relativity might not be the whole story. The conventional picture of gravitational collapse is grim. A massive star exhausts its nuclear fuel and can no longer support itself against its own gravity. the core collapses. In less than a second, matter that once spanned a volume larger than Earth crushes down toward a single point. According to classical general relativity, this collapse is inexorable. Nothing can stop it. The matter falls inward forever, creating a singularity, a point of infinite density where the known laws of physics break down. But Gastignaga's team argued that this picture ignores quantum mechanics. At the heart of their model is something called the Pauli exclusion principle. This is one of the foundational rules of quantum mechanics, discovered in 1925 by physicist Wolfgang Pauli. It states that no two identical fermions, particles like electrons, protons, and neutrons, can occupy exactly the same quantum state at the same time and place. You've benefited from the Pauli exclusion principle your entire life without knowing it. It's the reason matter is solid. It's why electrons and atoms arrange themselves in shells, rather than all piling into the lowest energy level. It's why white dwarf stars, the remnants of sun-like stars, can resist gravitational collapse. The electrons inside them refuse to be squeezed any closer together. The exclusion principle is also responsible for the stability of neutron stars. These incredibly dense objects, with masses comparable to our sun but squeezed into spheres only about 20 kilometers across, are held up by neutron degeneracy pressure. The neutrons, like the electrons in white dwarfs, resist being compressed beyond a certain density. But there's a limit. If you add enough mass to a neutron star, not even neutron degeneracy pressure can hold it up. The matter collapses further, forming a black hole. Or so we thought. Gastignaga's team showed that even inside a black hole, the exclusion principle still applies. It doesn't disappear just because you cross the event horizon. It prevents matter from collapsing to a point. As the density increases during gravitational collapse, particles are forced closer and closer together. Eventually, they reach a limit where the exclusion principle creates what amounts to a pressure barrier. The collapse halts. The key insight is that the exclusion principle becomes incredibly strong at extreme densities. As matter is compressed, the uncertainty in particle positions decreases. They're squeezed into smaller and smaller volumes. But the Heisenberg uncertainty principle says that when position becomes more certain, momentum becomes less certain. The particles start moving more energetically, creating an outward pressure. At the densities reached in a collapsing black hole, far beyond even neutron star densities, this quantum pressure becomes enormous. According to Gastignaga's calculations, it's enough to halt and reverse the collapse. We've shown that gravitational collapse does not have to end in a singularity. Gastignaga explained, "We found that a collapsing cloud of matter can reach a high-density state and then bounce, rebounding outward into a new expanding phase. This is the quantum bounce, and what emerges from the bounce looks remarkably like our own universe. The details of the bounce are fascinating. As matter compresses to extreme density, the quantum pressure from the exclusion principle grows exponentially. At some critical density, far higher than anything we can produce in laboratories, but lower than the infinite density of a classical singularity, the inward gravitational force is exactly balanced by the outward quantum pressure. For a brief, unimaginable instant, the collapse pauses. Everything hangs in perfect equilibrium. Then the quantum pressure wins. The matter, compressed as far as physics will allow, rebounds. The collapse transforms into expansion. What was falling inward is now flying outward. This transition from collapse to expansion happens over an incredibly short timescale, far shorter than the Planck time, the smallest meaningful unit of time in physics. To any observer inside, There would be no awareness of the transition. One moment, matter is collapsing. The next moment, it's expanding. The bounce is smooth and continuous at the fundamental level, even though it represents a complete reversal of the cosmos's direction. The mathematics shows that after the bounce, the matter inside the black hole begins expanding rapidly. This expansion naturally produces two phases of accelerated growth, one at the very beginning, corresponding to what we call cosmic inflation, and one much later, corresponding to what we call dark energy. In the standard cosmological model, both inflation and dark energy are mysterious. Inflation requires a hypothetical field called the inflaton that has never been observed. Dark energy constitutes about 68% of the universe's energy budget, yet we have no idea what it is. These are components we've had to add to our theories by hand, with no underlying explanation. In Gastignaga's model, both phases of accelerated expansion emerge naturally from the physics of the bounce itself. Even more surprisingly, the rebound naturally produces the two separate phases of accelerated expansion, inflation and dark energy, driven not by hypothetical fields, but by the physics of the bounce itself, he wrote. One of the most compelling aspects of this model is that it makes specific, testable predictions. The first prediction concerns the curvature of space. In the standard cosmological model, the universe appears to be very nearly flat, neither curved like the surface of a sphere, nor curved like a saddle. This flatness is itself a mystery requiring extreme fine-tuning in the early universe. Gastignaga's model predicts that the universe should be slightly curved, not by much. He estimates a curvature parameter of about 0.07, with an uncertainty of about 0.02. This corresponds to a very slight positive curvature, like the surface of an extremely large sphere. Current measurements from the Planck satellite show the universe is flat to within their measurement precision, but future experiments should be able to detect or rule out the small curvature that Gastignaga's model predicts. The second prediction concerns the cosmological constant, the parameter that describes dark energy's strength. In Gastignaga's model, the cosmological constant isn't arbitrary. It's determined by the physics of the bounce and has a specific relationship to the universe's curvature. The smoking gun for our bouncing scenario is the presence of both a small spatial curvature and a small cosmological constant term, the team wrote in their paper. Gastignaga is well positioned to test his own predictions. He serves as science coordinator for Arrakis, an upcoming European Space Agency mission designed to study the faint outer regions of galaxies. These outskirts are difficult to observe because they're so dim, but they contain what astronomers call the fossil record of galaxy formation, traces of how galaxies grew and evolved over billions of years. Arrakis will carry 4 wide-angle telescopes, 2 using near-infrared technology, 1 optical, and 1 covering the near-ultraviolet. Together, they'll create the most detailed maps ever made of galactic halos, the diffuse regions of stars and dark matter surrounding visible galaxies. If the universe really did begin with a gravitational bounce rather than a Big Bang, these halos might retain subtle signatures of that early era. The black hole universe model also offers a different perspective on dark matter. In the standard picture, dark matter is some kind of particle we haven't yet discovered, perhaps a neutralino or an axion. But Gastignaga suggests that some dark matter might instead be relics from the collapsing phase that preceded the bounce, matter that was present in the parent universe before it collapsed into the black hole that became our cosmos. It's possible that some forms of dark matter are connected to relics from the collapsing phase of our universe, but more work is needed to explore that idea, Gastignaga noted. Perhaps the most mind-bending implication of the Portsmouth study is what it says about the relationship between our universe and others. You can think of this like a nested structure. Black holes inside black holes like Russian dolls, Gaztanyaga explained to BBC Science Focus. Every black hole in our universe could contain its own cosmos, and our universe in turn exists inside a black hole that formed in some larger parent universe. This doesn't mean every black hole creates a universe as complex as ours. Large black holes, like the one we might inhabit, allow structure to form: galaxies, stars, planets. Smaller black holes lead to universes that expand or collapse too quickly for anything interesting to happen. The fact that we live in one of the rare, very large cases might not be a coincidence. It's the only kind of black hole universe where observers like us could exist. This is a version of the anthropic principle, but it's grounded in physics rather than philosophy. We're not special because the universe was designed for us. We're simply in the only kind of black hole universe that could have produced beings capable of asking questions about black hole universes. Gaztanyaga's work represents a significant advance in black hole cosmology because it provides a complete, mathematically rigorous description of how a bounce might occur using only well-established physics. Previous models, like Popowski's torsion-based theory, had proposed mechanisms for avoiding the singularity, but Gaztanyaga's approach uses only general relativity plus the basic principles of quantum mechanics. We now have a fully worked-out solution that shows the bounce is not only possible, it's inevitable under the right conditions, Gaztanyaga said. Not everyone is convinced, of course. The standard cosmological model, despite its mysterious components, has successfully explained decades of precision observations. It predicted the detailed structure of the cosmic microwave background before it was measured. It explains the abundances of light elements forged in the first few minutes after the Big Bang. It accurately describes the expansion history of the universe. Any alternative model has to match all of this success while also making new predictions that can distinguish it from the standard picture. Gaztanyaga believes his model does this. The predicted curvature is specific and measurable. If future observations find the universe to be exactly flat, the bounce model would be ruled out. But if they find a small positive curvature, if they detect that hint of spherical geometry in the shape of space, it would be powerful evidence that our universe didn't emerge from nothing. It would suggest that we live inside a black hole, the remnant of a gravitational collapse in some vaster reality we can never see. Let that number sink in for a moment. 40 quintillion. That's the estimated number of stellar mass black holes in the observable universe, according to a 2022 study published in the Astrophysical Journal. Written out, it looks like this: 40,000, 40 billion billion, 4 followed by 19 zeros. And that's just the stellar mass black holes, the ones formed from collapsed stars with masses between a few times and a few hundred times that of our sun. Add the supermassive black holes lurking at the centers of galaxies, at least one in nearly every large galaxy, and you have roughly another 100 billion more. If black hole cosmology is correct, every single one of these objects contains a baby universe. The implications are staggering. Our observable universe is approximately 93 billion light-years across, containing 2 trillion galaxies, 100 billion trillion stars, and more atoms than there are grains of sand on all the beaches of Earth. And that entire incomprehensible vastness might be replicated, in some form, inside every black hole we've ever observed. To put this in perspective, when astronomers photograph a distant galaxy and see a bright point at its center, a supermassive black hole, they might be looking at the exterior surface of a reality as complex as everything they can see around them. That single pixel of light in the image could represent a cosmos full of galaxies, civilizations, histories, and stories we will never know. The numbers become almost meaningless at this scale. If each of our 40 quintillion stellar mass black holes contains a universe with its own hundreds of billions of black holes, and each of those contains another universe, the multiplication explodes beyond comprehension. We could be describing more universes than atoms in our own cosmos, more realities than there are possibilities for arranging matter, more existence than we have numbers to count. Stephen Hawking explored this idea in his 1993 book, Black Holes and Baby Universes. It was, he said, among the most surprising implications of his work on black hole physics. Hawking's investigation into baby universes grew out of his famous discovery of Hawking radiation, the theoretical prediction that black holes slowly emit particles and eventually evaporate. When he analyzed what happens to the information that falls into a black hole, he was led to speculate about where it might go. Objects that fall into a black hole, Hawking speculated, might go off into a little baby universe of their own, a small, self-contained world that branches off from our region of space-time. These baby universes would exist in what he called imaginary time, at right angles to real time, in a realm where the beginning and end of the universe become indistinct. What would these baby universes look like from inside? If Popowski's model is correct, they would look much like our own universe. The matter falling into a black hole would reach extreme density, generate torsion forces, bounce, and begin expanding. From the perspective of any hypothetical beings living in that baby universe, their cosmos would appear to begin with its own Big Bang, never knowing that their beginning was actually a stellar collapse in apparent reality they could never observe. The baby universes are completely invisible to us. Once something crosses the event horizon of a black hole, no information about it can ever return. This is the fundamental nature of the one-way boundary we discussed earlier. Light cannot escape. Signals cannot escape. Nothing can tell us what happens inside. This creates a profound epistemological barrier. We can never know whether our theories about baby universes are correct by observing them directly. The event horizon enforces a kind of cosmic censorship, hiding whatever lies beyond from our view. This might seem like a flaw in the theory. If we can't observe baby universes, how can we ever test whether they exist? But science often deals with entities we cannot observe directly. We can't see electrons, but we infer their existence from countless experiments. We can't see the core of the sun, but we understand it through physics and neutrino detections. We can't see the early universe, but we read its traces in the cosmic microwave background. Similarly, baby universe theories make predictions about what we should observe in our own universe. The curvature predictions of Gastanyaga's model, the optimal black hole production of Smolin's cosmological natural selection, the galaxy rotation asymmetries of Shamir's analysis, all of these can be tested with observations entirely within our own cosmos. The baby universes themselves remain forever hidden, but their existence would leave fingerprints on the reality we can see. There's another twist involving time. From outside a black hole, watching an object fall toward the event horizon, something strange happens. Time dilation, predicted by Einstein's general relativity and confirmed countless times by experiment, causes the infalling object to appear to slow down as it approaches the horizon. It never quite reaches it. The object seems to hover at the edge, growing dimmer and redder, frozen at the threshold for eternity. This is an illusion created by our perspective. From the falling object's point of view, Nothing special happens at the horizon. It crosses in finite time and continues falling inward. But from our external viewpoint, the crossing takes forever. This means that if you watched a star collapse into a black hole, you would see it slow down and freeze just before the event horizon formed. The star's matter would appear suspended in time, never quite completing its collapse. And yet, from the matter's own perspective, the collapse happened long ago. The bounce occurred. The baby universe began its expansion. All of this could be happening right now, inside every black hole you can point a telescope at. Entire cosmoses are evolving, developing structure, perhaps spawning life, all hidden behind horizons we can never cross. This connects to one of the most mind-bending ideas in theoretical physics, the holographic principle, which we explored earlier. If the information content of a black hole is encoded on its surface, then in some sense, the three-dimensional baby universe exists as a pattern on the two-dimensional event horizon. The interior is the holographic projection. The boundary is the fundamental reality. This is deeply counterintuitive. We experience ourselves as living in three-dimensional space. We move forward and backward, left and right, up and down. Objects have volume. The world feels thoroughly three-dimensional. But the holographic principle suggests this experience might be, in some sense, an illusion. The true description of reality might be lower dimensional, with our three-dimensional experience emerging from a more fundamental two-dimensional substrate. For a baby universe inside a black hole, this would mean the entire cosmos, with all its galaxies, stars, planets, and conscious beings, is encoded on the event horizon surrounding it. The pattern of bits on that two-dimensional surface somehow contains all the information needed to describe a three-dimensional reality. From outside, looking at a black hole's event horizon, we might be looking at the outside of another reality, the spherical screen on which an entire universe is encoded. This connects black hole cosmology to some of the deepest questions in physics. What is space? Where does it come from? Is it fundamental? Or does it emerge from something more basic? The holographic principle suggests space might emerge from quantum information, that the three dimensions we experience are a kind of coding scheme for information stored in fewer dimensions. If true, this would mean the question, what's inside a black hole, has a surprising answer. Everything that appears to be inside is actually encoded on the surface. The interior is a perspective, a way of reading the information rather than a separate place. And if our universe is inside a black hole, then from the parent universe's perspective, everything we know and love is a pattern on a spherical surface a few kilometers or a few billion kilometers across. Our 13 billion years of cosmic history, our 2 trillion galaxies, our hopes and dreams and fears, all of it somehow on that horizon. Hawking went further, suggesting that baby universes might not simply branch off and disappear. They might reconnect to our universe somewhere else, appearing to us as a different black hole that formed and then evaporated. Particles that fell into one black hole would appear as particles emitted by the other black hole. This speculative idea remains unproven, but it hints at the possibility that black holes are not dead ends, but passages, wormholes connecting different regions of a vast multiverse. The concept of a fractal multiverse emerges from these ideas. Universes contain black holes. Black holes contain baby universes. Those baby universes contain their own black holes, which contain even smaller baby universes, and so on, potentially without limit in both directions. Are we at the top of this hierarchy? Almost certainly not. If our universe is inside a black hole, it's inside a black hole that formed in a larger parent universe. That parent universe might itself be inside a black hole in a still larger grandparent universe. The regression could continue indefinitely. And below us, the 40 quintillion stellar mass black holes in our universe might contain 40 quintillion baby universes, each potentially as rich and complex as our own. Some of those baby universes might already contain life. Beings in those universes might be having this exact same conversation, wondering what lies inside their black holes. Not all black holes are created equal, though. The size of a black hole determines how much time its interior universe has to evolve before it collapses or reaches heat death. A stellar mass black hole with 10 times the Sun's mass has an event horizon only about 60 kilometers across. From our external perspective, its Hawking radiation lifetime, the time it takes to evaporate, is about 10 or 67 years, an unimaginably long time compared to the 13.8 billion year age of our universe. But from the perspective of the baby universe inside, this might translate to a very different timescale. Cosmologists haven't yet worked out the exact relationship between external black hole time and internal baby universe time, but it's likely that smaller black holes give their interiors less time to evolve. A supermassive black hole, by contrast, might offer its baby universe billions or trillions of years of internal evolution. Plenty of time for stars to form, for heavy elements to be forged in supernova, for planets to coalesce, for life to emerge. The anthropic principle takes on new meaning in this context. We exist in a large universe because large universes arise from large black holes, and large black holes provide enough internal time for observers to evolve. Small black hole universes collapse or fade before anything interesting can happen. We're not special. We're just in the one kind of universe where creatures like us can exist. This explains, in a remarkably elegant way, why our universe appears fine-tuned for life without invoking any designer. We live in one of the universes, perhaps one of an infinite number, where the conditions happened to allow complexity to emerge. The others exist too, but they're sterile and observer-free. When you next see an image of a black hole, perhaps the famous Event Horizon Telescope image of M87H, a shadow of darkness surrounded by a ring of fiery orange light, consider what you might be seeing. That dark circle isn't just an absence of light. It might be the outer surface of a cosmos as vast and complex as your own. The darkness isn't empty. It's full of everything. Galaxies, stars, planets, and possibly minds looking back at their own sky, wondering what lies beyond. If the black hole universe hypothesis is so compelling, why isn't it the mainstream view? Why do most cosmologists still work within the standard Big Bang framework? The answer is that black hole cosmology, while intriguing, faces serious objections. Understanding these objections and the responses to them is essential for evaluating whether the theory has merit. Science progresses through criticism. Every theory worth its salt must withstand attacks from skeptics, refine itself in response to objections, and ultimately prove its worth against alternatives. Black hole cosmology has been subjected to this process for over 50 years, since Pathria first suggested the idea in 1972. The fact that it's still taken seriously says something about its resilience. But serious objections remain, and we need to confront them honestly. Let's start with the most well-known critique, articulated by physicist Sean Carroll in a widely read blog post titled, "The Universe is Not a Black Hole." Carroll, a cosmologist at Johns Hopkins University, known for his work on the arrow of time and the foundations of physics, laid out several technical arguments against the simplistic identification of our universe with a black hole interior. Carroll's critique is worth taking seriously precisely because he's not a fringe figure or a crank. He's a mainstream physicist with expertise in general relativity and cosmology. When someone of his caliber raises objections, the field listens. First, he noted that while the Schwarzschild radius of the observable universe happens to roughly equal the Hubble radius, this is a consequence of living in a spatially flat universe at critical density, not evidence of anything profound. The math works out this way because of how critical density is defined, not because our universe is literally inside a black hole. Second, Carroll pointed out a key difference between black holes and cosmology. A black hole is defined by what lies outside it. A black hole exists in contrast to the external universe from which it forms. But if our universe has no outside, if there's nothing beyond it, then calling it a black hole doesn't really mean anything. The space-time solution to Einstein's equation that describes a universe expanding from the Big Bang is very similar to the time reversal of a black hole, Carroll wrote. But you don't really learn much from making that statement, especially because there is no outside. Everything you wanted to know was already there in the original cosmological language. This is technically correct and highlights an important point. Black hole cosmology isn't claiming our universe is a black hole in the conventional sense. It's claiming our universe is the interior of a black hole that formed in a parent universe. That parent universe provides the outside that Carroll says is necessary for the concept to be meaningful. Carroll anticipated this response, but remained skeptical. Even granting a parent universe, he argued, the analogy breaks down when you examine the details of how space-time behaves. A standard black hole, formed from a collapsing star, has matter falling inward toward a singularity. The future of any object inside is to be crushed. But our universe is expanding. Matter is moving apart, not together. How can an expanding universe be inside a collapsing black hole? This objection sounds devastating, but has a straightforward resolution in models like Popowski's and Gastanyaga's. The key is the bounce. In these models, the matter initially does fall inward during the collapse. But the collapse reverses before reaching a singularity. The bounce transforms collapse into expansion. What looks like a black hole from outside, matter disappearing behind an event horizon, corresponds from the inside to matter expanding outward from an extremely dense initial state. The singularity objection is related. General relativity, in its classical form, predicts that gravitational collapse inevitably produces singularities, points of infinite density where the theory breaks down. The Penrose-Hawking singularity theorems, which we discussed earlier, prove this mathematically under general conditions. If singularities are inevitable, how can black hole cosmology avoid them? The answer lies in quantum mechanics. The singularity theorems assume classical physics all the way down. But at the extreme densities inside a collapsing star or at the Big Bang, quantum effects become important. Popowski's torsion creates a repulsive force that halts collapse. Gastanyaga's Pauli exclusion principle prevents matter from being squeezed past a certain density. Both mechanisms prevent the singularity from forming. This isn't ad hoc. It's what we should expect when quantum mechanics meets gravity at extreme scales. The singularity theorems don't prove that singularities actually exist. They prove that classical general relativity predicts singularities. Since we know classical physics breaks down at quantum scales, the theorems tell us where our current theories need modification. the cosmological principle presents another challenge. This principle states that the universe is homogeneous and isotropic on large scales. It looks the same everywhere and in all directions. Decades of observations support this. The cosmic microwave background is uniform to 1 part in 100,000. Galaxies are distributed fairly evenly throughout space. There's no obvious center and no obvious edge. A universe inside a black hole might seem to violate this principle. Black holes have a center, the singularity, or in bounce models, the point of maximum density, and a boundary, the event horizon. How can we reconcile cosmic homogeneity with this structure? The answer depends on where we are relative to the black hole's structure. If we're far from both the bounce point and the horizon, the universe could appear homogeneous on the scales we observe. The center of our universe, the location of the Big Bang Big Bounce, is 13.8 billion years in our past. We can't see it directly because the universe was opaque then. The event horizon, if our universe has one, is beyond our observable reach, perhaps coincident with the cosmological horizon we discussed earlier. Within our observable universe, the remnants of the bounce have been stretched and smoothed by expansion, producing the homogeneous conditions we observe. The black hole structure exists, but it's hidden from us by vast distances and deep time. What about the density objection? A black hole, by definition, has an enormous concentration of mass in a small region. That's what creates the extreme gravity. But our universe is mostly empty. The average density of the cosmos is only about 6 protons per cubic meter, essentially a vacuum. How can a black hole contain so much nothing? This objection seems compelling until you consider supermassive black holes. The black hole at the center of the M87 galaxy, famously photographed by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion suns. Its event horizon is larger than our entire solar system. But if you calculated the average density inside that event horizon, the total mass divided by the total volume, you'd get a surprisingly small number, roughly 0.006 kilograms per cubic meter. That's far less dense than air. For the largest supermassive black holes, with masses of tens of billions of suns, the average density inside the event horizon is less than that of water. So it's entirely possible, even expected, for a universe-sized black hole to have an extremely low average density while still being a legitimate black hole. The most philosophically interesting objection comes from the information paradox. When something falls into a black hole, what happens to the information that described it? Information here means more than data. It means the complete physical description of a system, all the quantum states and correlations that distinguish one configuration of matter from another. In classical general relativity, the information is destroyed at the singularity, gone forever. The matter that falls in becomes part of a featureless black hole characterized only by mass, charge, and spin. All the details of what fell in, whether it was a star or a spaceship, a library or a person, are irretrievably lost. But this violates a fundamental principle of quantum mechanics called unitarity, which says information is always conserved. In quantum mechanics, you can always, in principle, run the equations backward and reconstruct the past from the present. Information might get scrambled beyond practical recovery, but it can never truly disappear. For decades, physicists debated this paradox. Stephen Hawking initially believed information was truly lost, which would require modifying quantum mechanics. Most other physicists believed information must be preserved somehow, which would require modifying our understanding of black holes. The debate was fierce and personal at times. Hawking bet physicist John Preskill that information was lost, offering an encyclopedia as the stakes. In 2004, Hawking conceded the bet, admitting he'd been wrong. Information is preserved after all. Recent work on quantum extremal surfaces and holographic principles has largely resolved this in favor of information preservation. The information that falls into a black hole isn't destroyed. It's encoded on the event horizon and eventually released through Hawking radiation. The mathematics is complex, but the upshot is that black holes don't truly destroy information. They scramble it and slowly leak it back out. How does this affect black hole cosmology? Leonard Susskind, one of the architects of the holographic resolution to the information paradox, engaged in a famous debate with Lee Smolin about exactly this issue. Smolin's cosmological natural selection, which we discussed earlier, requires that information can pass from parent universes to baby universes. That's how physical constants can mutate slightly during black hole formation. But Susskind argued that information preservation prevents this. If information falling into a black hole is ultimately returned to the parent universe through Hawking radiation, it can't also be transmitted to a baby universe. The information can only be in one place. This is a serious objection. If Susskind is right, there's no mechanism for inheritance in cosmological natural selection. Without inheritance, there's no way for successful physical constants to be passed to offspring universes. And without that, the whole evolutionary framework collapses. Smolin has responded by noting that the information paradox resolution is still not fully understood. The holographic principle shows that information is preserved, but the exact mechanism by which it's preserved remains unclear. There might be room in that uncertainty for some information to pass to baby universes, while the rest returns to the parent. This remains an open question. Some physicists believe the holographic principle might actually support a kind of information transmission to baby universes through mechanisms we don't yet understand. Others believe it rules such transmission out. What everyone agrees on is that we don't yet have a complete theory of quantum gravity. Until we do, questions about what exactly happens inside black holes and whether baby universes can inherit information from parents will remain partially unresolved. Despite these objections, black hole cosmology persists as a legitimate research program. Gaztanyaga's 2025 paper was published in Physical Review D, one of the premier journals in physics. Popławski's work has appeared in peer-reviewed journals for over 15 years. Smolin continues to develop and defend cosmological natural selection. The theory isn't proven. It might be wrong, but it's not crackpot speculation. It's a serious scientific hypothesis that makes testable predictions, addresses long-standing problems in cosmology, and might ultimately reshape our understanding of where the universe came from. What does it mean if we're inside a black hole? This is the kind of question that can keep you awake at night if you let it. The implications ripple outward, touching on everything from the nature of reality to the meaning of existence. Let's explore them carefully. Let's start with what it doesn't mean. We're not trapped. We're not imprisoned in some cosmic dungeon. The event horizon that might surround our universe isn't a wall we're pressing against. For us, this is all there is. The interior of the black hole is our reality, the only reality we can access. Calling it a black hole changes our description of where we came from, but changes nothing about our lived experience. This point is important and often misunderstood. When people first hear about black hole cosmology, they sometimes imagine that we're somehow compressed or squeezed, living in a cramped space that's smaller than it should be. But that's not how black holes work. The interior of a black hole can be vast. Indeed, according to general relativity, it can be larger on the inside than it appears from outside. Space curves in ways that create more room, not less. Think of it this way. Learning that you're on a planet orbiting a star doesn't change what it feels like to walk outside in the morning. The sun still rises. The grass is still green. Your life proceeds unchanged by the astronomical context. Similarly, learning that your universe exists inside a black hole wouldn't change the laws of physics, the color of the sky, or the warmth of human connection. The universe would be exactly as big as it ever was. The stars would be exactly as far away. Your coffee would taste exactly the same. The only thing that would change is your understanding of the context in which all this happens. But while our experience wouldn't change, our understanding of our place in reality would transform profoundly. Consider the question of what's outside. If black hole cosmology is correct, there is an outside, the parent universe in which our black hole formed. But what is that parent universe like? We can never know directly. The event horizon prevents any information from crossing. We can't send probes. We can't receive signals. The parent universe is separated from us not by distance, but by the fundamental structure of space-time. We can speculate, though. If our universe is typical, if Smolin's cosmological natural selection has any validity, the parent universe probably looks roughly like ours. It would have galaxies and stars and planets, because those are the conditions that produce the most black holes. The physical constants might differ slightly, but not so much that atoms and chemistry become impossible. Somewhere in that parent universe, billions of years ago from their perspective, a massive star exhausted its fuel and collapsed, or perhaps a giant gas cloud compressed under its own gravity. Either way, an event horizon formed, and what we experience as the Big Bang was the interior of that collapse beginning its bounce into expansion. From the parent universe's perspective, our entire cosmic history, the formation of galaxies, the evolution of life, your reading of these words, is happening inside what they would see as a dark sphere a few kilometers or a few billion kilometers across, depending on how massive the collapsed object was. The mind recoils from this. 13.8 billion years of cosmic evolution, trillions of galaxies, the entire light cone of observable existence, all of it somehow inside what looks from outside like a black nothing. But this is no stranger than what we already accept about black holes. The singularity at the center of a stellar mass black hole exists in what is, from the perspective of an external observer, an infinitesimal point of space and infinite extent of future time. General relativity tells us that space-time can curve in ways that create far more interior than exterior. A black hole, properly understood, has more room inside than out. What about the infinite regress? If our universe is inside a black hole that formed in a parent universe, that parent universe might also be inside a black hole, and that grandparent universe inside another. Does the regression continue forever? There's no logical reason it has to stop. Each universe could be one level in an infinite tower of nested realities, each giving birth to the next through gravitational collapse. The mathematics of infinity is strange. An infinite regression doesn't actually require infinite time to have elapsed in any particular universe. Each level in the hierarchy experiences its own time, its own history, its own beginning and end. The tower could stretch upward forever without any level being infinitely old. This resembles certain ideas in mathematics about infinite sets. Just as the integers go on forever without requiring any particular integer to be infinitely large, the hierarchy of universes could continue without limit, without requiring any universe to have existed for infinite time. Some physicists find this troubling. An infinite regress feels like it doesn't explain anything. It just pushes the question of origins back indefinitely. Where did the first universe come from? If there's no first universe, doesn't that leave the existence of everything unexplained? Others find the infinite regress oddly satisfying. It avoids the need for a mysterious beginning, a first moment when something came from nothing. Instead, there was always something, always another level above, always a parent universe giving birth to children. The question, why is there something rather than nothing, loses its force if there was never a time when there was nothing. Or it could be cyclic. Perhaps the tower eventually loops back on itself, with some far-removed ancestor universe actually being our own, or a descendant of our own, connected through chains of black hole births that eventually close into a circle. This cyclic possibility is reminiscent of certain exotic spacetime geometries that physicists have studied. Closed time-like curves, wormholes, and other solutions to Einstein's equations allow for causal loops where the future connects back to the past. Perhaps the multiverse itself forms such a loop, with no beginning and no end, just an eternal cycle of creation and recreation. Or perhaps there's a first universe somewhere, one that arose through some mechanism that didn't involve black holes at all. Spontaneous creation from quantum fluctuation, perhaps, or eternal existence in some timeless state. That first universe would be the ultimate ancestor, the root of the cosmic family tree. Some physicists have speculated about a quantum foam at the Planck scale, where space and time themselves fluctuate randomly. Perhaps the first universe bubbled up from this foam, a random quantum fluctuation that happened to inflate and become a stable cosmos. And from that first universe, through billions of years of stellar evolution and gravitational collapse, came the black holes that spawned all the subsequent generations. We don't know. We can't know, at least not with current understanding. The event horizons separating nested universes are absolute barriers to information flow. This brings us to the anthropic principle, which takes on new meaning in this context. The traditional anthropic argument notes that our universe appears fine-tuned for life. The strength of gravity, the masses of fundamental particles, the cosmological constant, all seem precisely calibrated to allow stars to form, chemistry to occur, and life to emerge. Change any of these by small amounts, and you get a sterile cosmos. Critics of the anthropic principle find it unsatisfying. It seems to explain fine-tuning by simply noting that we wouldn't be here to observe a universe that wasn't fine-tuned. This feels circular, almost a tautology. Cosmological natural selection offers something more substantive. The universe isn't fine-tuned for life per se. It's fine-tuned for black hole production, and the conditions that maximize black hole production happen to overlap significantly with the conditions that allow life. Stars are the factories of both black holes and heavy elements. Both require long-lived galaxies and stable chemistry. The universe that produces the most descendants is also the universe most hospitable to observers. This is a genuinely elegant explanation. It takes one of the deepest puzzles in cosmology. Why does the universe permit observers like us, and transforms it from a mystery into a natural consequence of cosmic evolution? Think about it this way. If Smolin's theory is correct, universes have been reproducing through black holes for countless generations. Each generation, the universes that make the most black holes leave the most offspring. The physical constants that favor black hole production become increasingly common simply because those universes out-reproduce the others. Now, what conditions favor black hole production? You need massive stars, because massive stars are what collapse into black holes when they die. You need galaxies to form, because galaxies are where stars congregate. You need enough heavy elements for planets to form around stars, because those planets don't directly affect black hole production, but the same processes that make heavy elements, stellar nucleosynthesis and supernovae, are the processes that end in stellar black holes. In other words, a universe optimized for making black holes will necessarily also be a universe where chemistry can happen, where planets can form, and where life has a chance to evolve. We're not the goal, we're a byproduct, but we're a byproduct of exactly the conditions that cosmic selection would produce. This isn't circular, it's a genuine prediction. If Smolin's theory is right, we should expect our universe to be near optimal for making black holes, and we should be able to test whether small changes in physical constants would increase or decrease black hole production. Early tests have been suggestive, with the neutron star mass limit coming in near the predicted value, but not conclusive. The elegance of this explanation is that it doesn't require any fine-tuner. There's no intelligence choosing the physical constants. There's just generation after generation of universes, blindly reproducing, with the most fertile ones becoming increasingly dominant. It's natural selection on a cosmic scale, operating through the same Darwinian logic that produced the diversity of life on Earth. What about free will? Nothing in black hole cosmology specifically addresses the ancient debate about whether our choices are determined or free. The universe inside a black hole obeys the same physics as any other universe. If physics is deterministic, if the future is entirely fixed by the past, that's equally true inside a black hole universe as outside one. But there's a philosophical wrinkle. If our universe is one of countless universes, each spawning more through black holes, the question of what we mean by I becomes complicated. Are there other versions of you in other universes? If physical constants vary between universes, there probably aren't exact copies. But there might be beings similar to you, facing similar choices in countless baby universes throughout the vast multiverse hierarchy. Some physicists who take the many worlds interpretation of quantum mechanics seriously already grapple with these questions. In that framework, every quantum measurement splits the universe into branches, and every version of you exists in some branch. Black hole cosmology adds another layer to this picture. Not only do quantum branches multiply, but gravitational collapses create entirely new arenas for existence. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests that quantum mechanics describes a reality that's constantly branching. Every time a quantum system faces multiple possible outcomes, all outcomes actually occur. The universe splits, and different versions of you experience different results. If this sounds similar to the multiverse of black hole cosmology, that's because both ideas share a common thread: the notion that our observable universe is not all there is. But the multiverses are different in important ways. The many worlds multiverse consists of branches that differ in their quantum states but share the same fundamental laws and constants. The branches diverge when quantum measurements occur, but they all started from the same initial conditions. The black hole cosmology multiverse consists of separate universes that may have different physical constants, that arose through gravitational collapse rather than quantum branching, and that are separated by event horizons rather than quantum decoherence. Could both be true? Could we live in a many worlds multiverse that's also nested inside a black hole cosmology multiverse? There's no obvious reason why not. The two ideas operate at different scales and through different mechanisms. They might both be describing real features of a reality far stranger than either idea alone would suggest. Some cosmologists have begun exploring the intersection of these ideas. If quantum branching happens inside a universe that's inside a black hole, and baby universes also form through gravitational collapse, the total number of realities becomes staggeringly large, essentially infinite along multiple dimensions. What about the simulation hypothesis, the idea, popular in some circles, that our universe might be a computer simulation run by some advanced civilization? Interestingly, black hole cosmology and simulation theory are not mutually exclusive. A black hole universe could be simulated, or a simulated universe could contain simulated black holes that spawn simulated baby universes. The layers of reality multiply in both directions, but there's a sense in which black hole cosmology is more grounded than simulation theory. We know black holes exist. We know matter collapses into them. We know general relativity predicts complex interior geometries. The baby universe hypothesis extends known physics in speculative but consistent ways. Simulation theory, by contrast, requires us to posit vast computational machinery for which we have no evidence and no theoretical framework. Religious and spiritual perspectives on black hole cosmology vary. For some, the idea that our universe emerged from a prior universe through a natural process sits uneasily with creation narratives that invoke a divine creator making something from nothing. If the Big Bang was really a big bounce inside a pre-existing black hole, the creation of our universe was just a physical transformation, not a metaphysical beginning. This challenges one of the classic arguments for God's existence, the cosmological argument. In its simplest form, this argument says that everything that begins to exist has a cause. The universe began to exist, therefore the universe has a cause, and that cause is God. But if the universe emerged from a prior universe through gravitational collapse and bounce, it didn't begin from nothing. It had a physical cause in the parent universe. Of course, this just pushes the question back further. Even if our universe came from a parent universe, where did that parent come from? And if there's an infinite regress of universes, does that need explanation too? The deepest question, why is there something rather than nothing, isn't answered by black hole cosmology. It's just relocated. For others, black hole cosmology simply pushes the question of ultimate origins back further. If our universe came from a parent universe, where did the ancestor universe at the top of the chain come from? The need for an ultimate explanation, why is there something rather than nothing, remains. Some theologians might argue that an infinite regress of universes is precisely the kind of thing that requires a transcendent explanation. The whole chain of universes, taken together, is contingent. It didn't have to exist. And contingent things, even infinite chains of them, call out for a necessary being that grounds their existence. Still others find a strange resonance between black hole cosmology and certain mystical traditions. The universe giving birth to universes in an eternal cycle of collapse and rebirth echoes ideas of cyclical time and cosmic regeneration found in various spiritual frameworks. Hindu cosmology, for instance, speaks of vast cycles of creation and dissolution, with universes arising and passing away over timescales that make our 13.8 billion years look like an eye blink. The concept of a cosmic breath, expansion, followed by contraction, followed by expansion again, bears some resemblance to the bounce model. Buddhist philosophy speaks of dependent origination, the idea that everything arises in dependence on other things, with no first cause and no ultimate ground. An infinite hierarchy of nested universes, each arising from gravitational collapse in its parent, fits surprisingly well with this worldview. Even in Western traditions, there are precedents for thinking of creation as an ongoing process rather than a one-time event. Process theology, influenced by philosopher Alfred North Whitehead, sees God as participating in an evolving universe rather than standing outside it as a detached creator. Black hole cosmology, with its picture of universes continually giving birth to new universes, resonates with this dynamic view. Perhaps the most important implication is humility. For centuries, humans have had to revise their understanding of their place in existence. We learned Earth isn't the center of the solar system. We learned the sun isn't the center of the galaxy. We learned the Milky Way isn't the only galaxy, or even a special one. Black hole cosmology continues this tradition. Our universe might not be special either. It might be one of countless universes, one branch in an infinite tree, one frame in an endless cosmic movie. The Big Bang that seemed so singular and momentous might be a routine event, happening inside black holes throughout the multiverse all the time. This doesn't diminish us. It contextualizes us. We are small in a way that's hard to comprehend, not just in space, not just in time, but in the very hierarchy of existence. And yet we're here somehow, asking these questions. The fact that we can even contemplate our place in such vastness is itself remarkable. We've traveled far together. From the Eastern Front of the First World War, where Karl Schwarzschild discovered the mathematics of black holes while calculating artillery trajectories, to the gleaming mirrors of the James Webb Space Telescope, searching for patterns in the rotation of ancient galaxies. From Roger Penrose's proof that singularities are inevitable in classical physics, to Nikodym Popławski's demonstration that torsion might make them avoidable. From the comfortable certainty that the Big Bang was the beginning, to the unsettling possibility that it was merely our beginning. One bounce among countless others in a multiverse that might have no beginning at all. We've explored mathematics and philosophy, observation and speculation. We've confronted ideas that stretch our intuitions to their limits and perhaps beyond. The journey has taken us through a century of physics. Einstein revolutionized our understanding of space and time, showing that they were not fixed stages on which events play out, but dynamic entities that bend and warp in response to matter and energy. Schwarzschild applied Einstein's equations to a point mass and discovered a solution so strange that Einstein himself resisted its implications. Hawking and Penrose proved that singularities lurk in that solution, points where physics as we know it breaks down. And a new generation of physicists, Popławski, Gastanyaga, Smolin, and others, have begun to explore what might replace the singularity if quantum effects are taken into account. What have we learned? First, that the question, what if our universe is a black hole, is not as absurd as it sounds. The mathematics of general relativity allows for it. The Schwarzschild radius of the observable universe does match the Hubble radius, a coincidence that might be meaningful or might be a consequence of how we define our terms. But either way, the universe and a black hole have more in common than we might have guessed. The similarities go beyond just the numbers. Both black holes and the observable universe have horizons. boundaries beyond which information cannot pass. Both involve extreme curvature of space-time. Both emerged from processes of gravitational compression. The language we use to describe one often applies to the other. Second, that the Big Bang has problems. The horizon problem, the flatness problem, and the monopole problem all suggest that the simple picture of an explosion from a point requires modification. Cosmic inflation fixes these problems, but inflation itself raises new questions about what caused it, what sustained it, and what came before it. Third, that alternatives exist. Popowski's torsion-based model uses the Einstein-Cartan theory to generate a bounce instead of a singularity, naturally producing inflation and potentially explaining our universe as the interior of a black hole in a parent universe. Gastignaga's 2025 paper shows that quantum mechanical pressure from the Pauli exclusion principle could produce a similar bounce, with testable predictions about the universe's curvature. Fourth, that new observations are tantalizing. Shamir's analysis of galaxy rotations in the JWST deep field shows an unexpected asymmetry that could be explained by our universe having a preferred rotation axis. Exactly what we'd expect if it inherited angular momentum from a spinning parent black hole. The CMB's axis of evil points in the same direction, though interpretation remains controversial. Fifth, that serious objections remain. The theory's relationship to the information paradox is unclear. The cosmological principle seems to conflict with having a cosmic center and edge, and the mainstream view remains that we don't need black hole cosmology to explain what we observe. Standard inflation plus dark energy works well enough. Where does this leave us? In science, the proper attitude toward an unproven hypothesis is neither belief nor dismissal, but continued investigation. Black hole cosmology makes specific predictions. It predicts that the universe should be slightly curved. It predicts that the conditions for black hole formation should be near optimal given the physical constants. It predicts that if the galaxy rotation asymmetry is real, it should correlate with a cosmic preferred axis. The next decade of observations will be crucial. Future observations will test these predictions. The European Space Agency's Arrakis mission will study galactic halos with unprecedented precision. This spacecraft, carrying 4 wide-angle telescopes operating in the near-infrared, optical, and near-ultraviolet, will map the faint outskirts of galaxies where the fossil record of their formation is preserved. If our universe really did begin with a gravitational bounce rather than a Big Bang, those outer regions might retain subtle signatures of that origin. Next-generation CMB experiments will improve constraints on curvature and isotropy. The Simons Observatory, under construction in Chile's Atacama Desert, will measure the cosmic microwave background with unprecedented precision. The proposed CMB-S4 experiment would go even further, deploying hundreds of thousands of detectors to map the polarization of the primordial light. If there's a small positive curvature to space, the signature Gastignaga's model predicts, these experiments have a good chance of finding it. Gravitational wave detectors will map black hole populations throughout the universe. LIGO and Virgo have already detected dozens of black hole mergers, and the upcoming LISA space mission will extend this capability to supermassive black holes. By understanding how black holes form and merge across cosmic time, astronomers can test whether the conditions in our universe really are optimized for black hole production, as Smolin's cosmological natural selection predicts. The James Webb Space Telescope continues to survey the distant universe, and follow-up studies on galaxy rotations will test whether Shamir's asymmetry holds up across larger samples and different regions of the sky. If the clockwise excess is real and cosmic, not just an observational bias, it should appear consistently regardless of where you look. If these observations confirm the predictions, black hole cosmology will move from speculation toward acceptance. If they refute them, the theory will fade into history as an interesting but ultimately incorrect idea. That's how science works. The beauty of this situation is that we don't have to wait long. The observations are already being made. The data is accumulating. Within a few years, we'll know much more about whether space is curved, whether the galaxy rotation asymmetry is real, and whether the conditions in our universe really are special in the ways black hole cosmology suggests. But regardless of whether the theory is proven true, the journey of asking the question has value. To wonder whether we live inside a black hole is to stretch our minds toward possibilities we might never have considered. It's to recognize that the universe we see might not be all there is, that reality could be vaster, stranger, and more layered than our everyday experience suggests. The question teaches humility. We evolved on the surface of one planet, orbiting one star in one galaxy, in what we assumed was the only universe. Each expansion of our cosmic perspective has required adjusting our sense of importance downward. Black hole cosmology continues this tradition, suggesting that even our entire observable universe might be one nested bubble in an endless foam of existence. The question teaches wonder. Every black hole you see in an image might contain a cosmos. Every supernova that creates a stellar remnant might be a birth event for a new reality. The universe isn't just vast in the direction we can see. It might be vast in dimensions of existence we can never access, stacked infinitely deep in the hierarchy of creation. And the question teaches us something about the nature of science itself. The greatest discoveries often come from asking questions that seem almost too strange to be serious. What if time is relative? What if matter is made of waves? What if the universe started in a hot, dense state? Each of these questions led to revolutionary insights because someone was willing to pursue the implications of ideas that challenged common sense. Whether or not we live inside a black hole, we live in a universe that rewards curiosity. Every question asked opens doors. Every theory tested, even if refuted, teaches us something about what's true. Look up at the night sky tonight. See those points of light, the distant suns around which unknown worlds might orbit. Beyond them, too faint to see, are the galaxies. 2 trillion of them in the observable universe, each with its hundreds of billions of stars. And within that vastness, within the dark cores of countless galaxies and the remnants of exploded stars, are the black holes. 40 quintillion of them, maybe more. Each one a horizon beyond which something happens, something we can describe mathematically, but can never observe directly. Perhaps those horizons surround emptiness, singularities where everything ends. Perhaps they surround baby universes, cosmoses as real and rich as our own, populated by beings who look up at their own sky and wonder about their own origins. We don't know yet. We may never know with certainty. But we can ask, we can calculate, we can observe and measure and test. We can push our understanding toward the edges of what's knowable, and sometimes a little beyond. That's what it means to be curious creatures in a mysterious universe. That's what it means to be human. And if someday we prove that we do live inside a black hole, it will be just another chapter in the long story of discovering how much bigger reality is than we ever imagined. The story never ends. The questions never stop. The universe, or multiverse, or whatever hierarchy of existence we ultimately inhabit, keeps revealing new layers of wonder. We are small. We are temporary. We are confined to a thin film of atmosphere on a rocky planet orbiting an ordinary star. And yet, here we are, contemplating the possibility that our entire cosmos is a single bubble in an infinite ocean, asking what lies beyond, searching for truth in the patterns of starlight and the equations of physics. That's not nothing. That's everything. The journey of asking the question, whether or not we ever answer it definitively, has changed us. We've had to think about what it means for something to be inside something else when space itself can curve. We've had to grapple with infinities, with nested realities, with the possibility that every single point of darkness in the night sky might contain as much existence as everything we can see. Our minds have stretched. Our imaginations have expanded. We've looked at black holes and seen not just exotic objects to be studied from afar, but potential mirrors of our own cosmic situation. We've looked at the Big Bang and wondered if beginning is even the right word. Science does this. It takes our everyday intuitions, forged by millions of years of evolution in a specific environment, and forces them to confront realities those intuitions never evolved to handle. The Earth isn't flat. Time isn't absolute. Empty space isn't empty. And perhaps the universe isn't everything. Whether black hole cosmology turns out to be true or false, the conversation it has sparked matters. It has forced physicists to think more carefully about the nature of singularities, about the role of quantum mechanics in gravitational collapse, about what it means for one region of space-time to be inside another. These are deep questions that would be important regardless of any specific theory's fate. And for those of us who are not professional physicists, the conversation offers something valuable too, a sense of the vastness and strangeness of reality, a reminder that the universe is not obligated to be comprehensible on human scales, and an invitation to wonder. Look up at the night sky tonight. See those points of light, the distant suns around which unknown worlds might orbit. Beyond them, too faint to see, are the galaxies, 2 trillion of them in the observable universe, each with its hundreds of billions of stars. And within that vastness, within the dark cores of countless galaxies and the remnants of exploded stars, are the black holes, 40 quintillion of them, maybe more. Each one a horizon beyond which something happens, something we can describe mathematically but can never observe directly. Perhaps those horizons surround emptiness, singularities where everything ends. Perhaps they surround baby universes, cosmoses as real and rich as our own, populated by beings who look up at their own sky and wonder about their own origins. We don't know yet. We may never know with certainty, but we can ask. We can calculate. We can observe and measure and test. We can push our understanding toward the edges of what's knowable, and sometimes a little beyond. That's what it means to be curious creatures in a mysterious universe. That's what it means to be human. And if someday we prove that we do live inside a black hole, it will be just another chapter in the long story of discovering how much bigger reality is than we ever imagined. The story never ends. The questions never stop. The universe, or multiverse, or whatever hierarchy of existence we ultimately inhabit, keeps revealing new layers of wonder. 100 years ago, most scientists believed our galaxy was the entire universe. 50 years ago, the Big Bang was still a controversial idea. 20 years ago, we had never detected a gravitational wave or photographed a black hole. The pace of discovery is accelerating, and the ideas we consider speculative today may be the accepted wisdom of tomorrow. or they may not. Science makes no guarantees. Theories rise and fall based on evidence, and black hole cosmology might ultimately join the list of intriguing ideas that turned out to be wrong. That wouldn't be a failure. It would be science working as it should, separating truth from appealing speculation through the hard work of observation and test. Either way, the journey matters. We are small. We are temporary. We are confined to a thin film of atmosphere on a rocky planet orbiting an ordinary star. And yet here we are, asking the biggest questions we can imagine, reaching toward understanding with the limited tools of language and mathematics and experiment. That's not nothing. That's everything there is.